So now we will start. So as I mentioned, so we have already seen in the last 3 lectures, we have already seen what is intermediate code, what is static single assignment form, SSA form, okay, and also local optimization. We have already seen liveness analysis, available expression analysis, and you can see you dead code elimination. Okay, so all these concepts we have already seen in the last 3 lectures. Okay, so in this lecture, actually, I want to cover the remaining points. Okay, basically some points were left out in the last 3 lectures. So those points I will cover, and some revision type of thing. Okay, we will do. So basically, this is the lecture outline. What we are going to study in this lecture, let me tell you. So first, we will study intermediate code. Okay, why we need intermediate code. So basically, in this intermediate code, we are going to study. First thing, we will study why. Okay, what is the need of intermediate code. The second, we will study okay, the types of intermediate code. Okay, what are the types. Okay, and then third, we will study some specific type. There is a specific type. There are some types, for example, 3 address code. Okay, and you can see abstract syntax tree, and there is DAG. Okay, so these are some types, and you can see SSA. This we have already studied. This we have already studied. But what is this? What is this? So these 2 points we will study: abstract syntax tree and DAG. Okay, directed acyclic graph. So this is what we are going to study in this intermediate code. Okay, and also there is another intermediate code. This is control flow graph. This we have studied. Okay, so basically these are the intermediate code. All these are the intermediate code. This we have already studied. Okay, the control flow graph. This we have already seen. Okay, so these are the topics that are remaining. Okay, abstract syntax tree, DAG. Okay, so these 2 topics we will study, and of course I will also take some examples of control flow graph. So if anyone has any doubt in control flow graph, you can ask at that time. Okay, okay. So next, what we will study is why. Okay, what is local optimization. Okay, so this is what we are going to study: local optimization. In this local optimization, again we will study where. Okay, so the first point, where. Okay, then the second point, why. Okay, why we do optimization, where we do optimization. Okay, and the third we will study is, okay, what basically what is types of optimization, types of optimization. And then we will study some analysis. Okay, we will see liveness analysis and available expression analysis. Okay, available expression analysis. Okay, so these 2 we have already seen, actually. Okay, these 2 concepts we have already seen in the last 3 lectures. Okay, so the playlist I already shared with you. If there is anyone who has not watched the last 3 lectures, okay, so send me a message. Okay, and basically, okay, you can ask for the playlist, and I will share with you. So basically, on the YouTube channel of Go Classes, you can find all these lectures you can find on the YouTube channel of Go Classes. Okay, so basically just go to Go Classes YouTube channel, Go Classes. Okay, for GATE CSE. Okay, so on this channel you will find, so this is the YouTube channel. Okay, this is the YouTube channel. On this channel you will find all these lectures. Okay, so on this YouTube channel, basically, okay, all these lectures you will find. Okay, okay, so these are the points. Now let's start. Okay, so first, you already know this is the compiler phases. Okay, phases in a compiler. So you already know all these points. So basically, in a compiler is a very big program. Okay, since it is a very big program. Okay, so basically we divide this compiler in some phases so that we can study compiler very easily. Okay, so these are the phases. This lecture will be added in the playlist. Yes. Okay, so this lecture also will be added in this playlist, but tomorrow, not today. Okay, so in the live class you can ask your doubts. If you have any doubts, you can ask. So basically, let me quickly give you overview. Okay, I'm not going to teach all these pages, but let me give you the overview. The overview is this, that these are the phases of the compiler. Okay, so you can notice, so there is lexical analyzer, syntax analyzer, semantic analyzer, intermediate code generator, and then we have, okay, code optimizer, machine independent code optimizer, and then code generator, and then machine dependent code optimizer. So these are the phases of the compiler. In these are the, this is the front end. This is known as front end. Okay, so basically this is your front end, as you can see, front end. Okay, front end. So these four phases you can see, these are the front end, and these three phases, okay, these are the back end. Okay, so now let's see. So basically again, this is the same diagram, but you can notice here what is the front end. So you can notice the lexical analyzer, the another name is scanner, lexical analyzer, parser, and semantic analyzer. Okay, so these are the front end, and you can see. And what are the back end? So the code generation, this is the back end. Okay, now the why, okay, what is the difference between front end and back end? Can anyone tell me? Can anyone tell me what is the major difference between front end and back end? Just tell me this point. Okay, what is the major difference? Okay, so basically this is my first question today. What is the difference between front end and back end? What is the difference? What is the major difference between front end and back end? What is the major difference? Compiler dependent, compiler independent. No, Amar, both are see, both are the phases of compiler. In a compiler, this is your compiler. In this compiler, this is your compiler. In this compiler, there is a front end. Okay, so there are, this is the front end, this is the front end, and this is the back end. What is the major difference between front end and back end? This is what I'm asking. Okay, so let's see. So yes, some students have given correct answer. Hiren has given correct answer. Masi, okay, so let me answer this. Basically, front end. Okay, let me tell you. This front end is actually, it depends on the source language. Okay, so this front end depends on the source language, and back end depends on the machine. Okay, on which basically the architecture, the machine. Okay, the platform. So basically, this depends on the machine, and this depends on the source language. So this is the difference between front end and back end. So you can notice this is an important line. The front end actually depends mainly on the source language. Okay, and the back end depends on the target architecture. Okay, on the machine, on the machine on which you are running your program. Okay, so is this clear to everyone? Front end, this front end will depend. For example, if you are making a C compiler, okay, if you are making a C compiler, then for this C compiler, this front end will depend on the syntax of C. So this front end basically deals with the syntax of C. I can say deals with the syntax of C or properties of C language. Correct? So this deals with the properties, or I can say syntax semantics of, okay, syntax semantics of, I can say syntax comma semantics. Okay, syntax comma semantics of C language, because this is our source language. Okay, so this is our source language. So what I'm saying is front end actually deals with the properties of C language. Okay, for example, lexical analyzer, parser. Yes or no? In this front end, as you can see, there is a lexical analyzer. There is a okay, you can notice there is a parser. Okay, there is a parser, and there is a semantic analyzer. Okay, and you can notice, and there is an intermediate code generation. Okay, so basically all these actually they deal with the properties of C language. So basically these phases depend on C language. Yes or no? Is this clear to everyone? These phases depend on C language. These phases actually don't depend on the target architecture. So they depend on C language, not on target architecture. Target machine, or I can say, okay, so not on target machine. Is this clear? Basically not on target hardware or machine, whatever you want to say. So basically this front end depends on this. And what is the back end? And back end actually depends on, okay, this back end, okay, this back end actually depends on the machine. So this back end means in this back end we have this, okay, code generator. So basically this code generator actually this depends on the target machine. This depends on target machine. Yes or no? Is this difference clear? There are many other differences, but is this particular difference clear to everyone? Okay, so And let me ask you one thing, that when we are studying something, ask your doubts related to that. Okay, for example, right now we are not studying liveness analysis. We will study after some time. Okay, we will study liveness analysis, but at that point of time you can ask the doubt from liveness analysis. So whatever we are learning right now, you ask your doubts from that topic. Okay, at the end of the class you can ask any doubt. Okay, is this clear? So this is the difference between front end and back end. This is the main difference, I can say. Okay, so this is the point. Now you can notice. Now this is my another question. This is the question number 2. Why we need intermediate code? Okay, basically without intermediate code, why? Okay, what is the reason we need intermediate code? Can anyone tell me why we need intermediate code? Basically, why don't? Okay, let me tell you. Okay, for example, here this intermediate cause. Okay, this part, why do we need this? Why we need intermediate representation? Why we need this is the question. Okay, so can anyone tell me what is the answer? Okay, so let me explain this. Okay, many students know the answer for portability reason, but what that means? Okay, see, many students know that answer is portability. Okay, reusability. Okay, so the answer is that is fine. Okay, so I can say answer is portability of a front end, I can say. Okay, answer is portability. But what that means, portability of a front end, I can say portability of front end, or I can say portability of compiler, or overall compiler, I can say. Okay, portability of compiler. Okay, so what that means, and actually, and also, okay, ease of optimization. I will explain all these points. I will explain. So why we need this intermediate code, let me explain. If we don't have intermediate code, then what will happen? Okay, so basically, anyway, this is right now we will not worry about the optimization phase. Okay, so don't worry about the optimization phase right now. Okay, but the point is simple. These, they depend on the source language. Okay, so these are source language dependent, and these, they depend basically. Okay, this depend on target machine. So this you already know. Now, if we don't have intermediate code, okay, if we don't have any intermediate language, okay, if we don't have any intermediate person, for example, okay, let me so let me tell you, if we don't have intermediate code, then what will happen? Without intermediate code, what will happen? So this is the point. Okay, you have front end. Okay, for example, you have a C language, you have Java language. Okay, and some other languages. Okay, so let me write it. Language L1, L2. Okay, so let's assume you have these languages L1, L2, L3, L4. Okay, so these are the languages. Now, as I told you, front end depends on the language. Yes or no? Correct. Front end, this front end depends on the property of the language. For example, C language, Java language, C++ language. So this front end depends on the property of language. Okay, so for each language we have a front end. Yes, so let me write it. F1, F2, F3, F4. These are the front end, and they depend on L1. This front end depends on, okay, this front end depends on this front end depends on this. Okay, so this we have already seen. Front end depends on the language, source language. Okay, C language front end will depend on the C language. Okay, C++ language front end will depend on the C++ language. Okay, because in the front end, what you have grammar. When you do the parsing, then you need grammar. Okay, and the grammar is what? Grammar defines the syntax of a language. Yes or no? So when you do parsing, if you are making a parser for C++ language, then you need a grammar for C++ language. Correct? Am I right? Okay, so basically this front end, this depends on the language. Now, if you don't have any intermediate code, okay, so now then what will happen? So you have target machine. Let's assume these are the target machines. Okay, so you have machine M1, you have machine M2, you have machine M3. Okay, so these are the target machine. Now, if you don't have this, I can say front end, sorry, intermediate code. If you don't have intermediate code, then what is going to happen? So we need 4 front end. That is fine. Okay, but also let me tell you that this is the target machine. This target machine has no knowledge of the language. Yes or no? Correct. So this target machine M1, this target machine has no knowledge of language. Correct. But this front end depends on the language. So this front end depends on the source language. This front end depends on this language. This front end depends on this language. But this machine has no knowledge of any of these languages. this machine does not know how to deal with these front ends, correct? Am I right? So what we will have to do, we will have to create a compiler for this combination. For this combination, we have to write another compiler. Okay, like on this machine M1, if you are okay running this, if you are writing a code in this language L1, then we need another compiler. For this combination, we need another compiler. For this combination, we need another compiler. For this combination, we need another compiler, another compiler, another compiler, like this. Yes or no? Is this clear to everyone? Is this point clear? So you can notice that this we will have to do if we don't have okay any intermediate code. There is no mediator. Okay, there is no mediator. Then this is what we will have to do. Okay, and also so I can say there are 4 front ends. Okay, there are 4 front ends. So these we will have to write. Okay, 4 front end code. Okay, coding. We will have to do the coding. So we have to write this code, this code, this code, this code. Okay, 4 codes. Okay, so these we have to do, and also we need 12. Okay, 12 codes for this, I can say generator, 12 code generators. Okay, final machine code generator, I can say. Okay, so 12 machine code generators we need. What I can say, 4 into 3 machine code generators we need. Also, there is one more thing. There is a phase called optimization phase. Okay, optimization. Now, optimization means improving the program. This you already know. Optimization simply means, okay, remember, optimization simply means, this we have already seen in the last class. In the last 3 lectures, we have already seen optimization means basically improvement of program. Improvement of program. Okay, and this improvement means basically, okay, time, improvement in time, okay, improvement in space, okay, and etc. Okay, so basically improvement in the program. So there is optimization phase. Tell me how many optimizer we need. How many? If we don't have an intermediator, there is no intermediate code, then how many optimizer we need? Tell me how many optimizer we need here. Anyone? How many optimizer we need? So again you can notice that here we need, again, for each combination we need another optimizer. Okay, for example, for this combination, what is the optimizer? For this combination, what is the optimizer? For this combination, optimizer. Okay, because let me tell you one more thing. Optimization, okay, this is done 2 times actually. Okay, I will tell you where this is done. I will tell you, but let me tell you that optimization is machine dependent also and machine independent also. There are 2 type of optimization: machine dependent and machine independent. Okay, so you can notice that we need 12 optimizers. So these many optimizers we need. So this is the cost. Okay, these many things we need. But if we have intermediate code, then what we need? Let's assume there is an intermediate language. Okay, let's assume there is some intermediate language. Okay, and let us assume that intermediate language is your assembly language. Okay, you already know in computer organization you study assembly language. Okay, so basically let us assume that intermediate language is assembly language. Actually, let's assume intermediate language is some assembly language. Means what it means? Tell me. Assembly language means it does not depend on the machine. It does not depend on the C language. Yes or no? So basically you have a source language, you have a C language. Let's assume you have this C language. From this C language, you create assembly language, this intermediate language, and let's assume intermediate language is some assembly language. Okay, some high level assembly language. So basically this intermediate language you have. Now remember, there is one interesting point here. This intermediate language actually does not depend on the source language, and this does not depend on the machine also. So this intermediate language does not depend on machine also, and this does not depend on source language also. So this is your code generation. Now what will happen? So because this is independent of all these things, okay, this is some maybe this can be anything. This is a fixed language, okay, fixed type of language. Okay, maybe 3 address code, maybe 3 address code. It depends on you which intermediate language you want. That depends on you. I will tell you what are the different type of intermediate languages we have. Let us assume 3 address code. Now this 3 address code does not depend on C language. This does not depend on the machine. Okay. Okay, so this is the point. Now with the intermediate code, what will happen? This is going to happen that we need 4 front ends. Yes, that is fine. Okay, so with we have this language L1, L2, L3, L4. And what we need front ends f1, f2, f3, f4. This is what we need. Yes, because front end depends on the source language. So this is what we need. There is no problem here. And now what will happen? Okay, this is C language, this is language. Okay, but we need what we need finally intermediate code. Okay, 3 address code. So what we will do now, we are writing 3 address code. Now just tell me this point. Okay, just tell me one more thing, that this intermediate code we are writing, finally we are writing 3 address code. This is your 3 address code. Okay, so 3 address code we have. Now what we need, we basically want intermediate code here. Okay, so this intermediate code we want here, let me call it IC. This intermediate code we want here, this intermediate code we want here, this intermediate code we want here. Now you can notice, because these intermediate codes, they are 3 address codes, because they are 3 address codes. So finally what we can do, we only have to deal with the intermediate code. Now the machine, okay, this platform, I can say machine M1, machine M2, machine M3. This machine only has to deal with the intermediate code, and the intermediate code is only 3 address code. So this machine only have to deal with the 3 address code, nothing else. Okay, so finally what we need 4 front ends. Okay, and what we need only 3 code generators, because this machine, they only have to deal with this intermediate code. Okay, this intermediate language, this is your intermediate language. Okay, so you can notice this is your intermediate language. So that is the reason we need 4 front ends, we need 3 code generators, and only one optimizer. If we are doing optimization on this intermediate code, so on this intermediate code we will do optimization. Okay, so then we only need one optimizer. Okay, so this is the benefit of intermediate code. Okay, so you can notice the benefit is this, that this improves the portability of the front end. This intermediate code will improve the portability of the front end, because now what you can do, now this front end you can apply on this machine, on this machine, on this machine. Okay, this front end you can directly apply on this machine, on this machine, on this machine. Okay, you don't have to write different front ends. Okay, are you getting my point? So basically this will, I can say, this front end now you can directly apply on this machine, this machine, this machine. So that is the point what I was saying, that it will improve the portability of the, portability means basically reusability. Okay, I can say portability, this simply means reusability. You don't have to write different codes. So this portability or reusability of the compiler of the front. So this is why we need intermediate code. Okay, so you can read this theory. I will share these slides. Okay, you can check it out. Now, what are the types of intermediate code? Okay, so can anyone tell me what are the type of intermediate code? So some types you already know. I already taught in the last 3 lectures. I have already taught you some types. So what are the intermediate languages? First of all, intermediate languages or intermediate code, or you can say intermediate language. Okay, first of all, let me tell you that we have different type of intermediate code. This is your choice. Like, okay, what type of intermediate you want, that is your choice. Okay, for example, some popular intermediate languages, let me tell you. Okay, so some popular intermediate codes, let me tell you. One is 3 address code. Okay, so there is 3 address code. There is something called 3 address code. Okay, this 3 address code, and this 3 address code can be implemented in 3 different ways. Okay, so these are the implementations of 3 address code: quadruple, triple, indirect triple. Okay, indirect triple. So these are the different implementations of 3 address code. Actually, let me tell you one thing. This 3 address code is actually a concept. Okay, this is actually a theory. Actually, this is a theoretical concept. And this theoretical concept can be implemented. These are the actual implementations. These are the actual ways of implementing them, of implementing 3 address code. Okay, so if I ask you, can I say 3 address code is intermediate code? Yes. Okay, can I say triple is intermediate code? Tell me, can I say triple is intermediate code? Can I say this triple is intermediate code? Yes, this is also intermediate code, because remember, this 3 address code is just theoretical concept. Okay, and remember, this is also intermediate code, this is also intermediate code, this is also intermediate code. Okay, some authors they actually they directly teach quadruple, triple, and indirect triple. So let me tell you, this is also intermediate code. This is also intermediate code. So if they ask you, is this intermediate code? Yes, this is intermediate code. Okay, this is intermediate code. This is intermediate code, and this is also intermediate code. Okay, another, what else we have? What else we have? Second, so this is most popular this is most popular, this 3 address code. This is the most popular intermediate code. This is the most popular intermediate language. Okay, and the second is what we have. There is syntax tree. This we will study, don't worry, this we will study. There is something called syntax tree. Okay, another variant of it, syntax tree, and there is a special type of syntax tree, that is DAG. This is a special type of syntax tree. Okay, another parse tree, your parse tree. Okay, so this is also there. This syntax tree, let me tell you here. Okay, but I will come back to this point. This syntax tree is also called, by default, syntax tree means abstract syntax tree. I will explain what this means, don't worry. I will explain what this means, abstract syntax tree. So whenever they say syntax tree, this means abstract syntax tree. And what this parse tree is, the another name of parse tree is concrete syntax tree. The another name of parse tree. And what is the difference? I will tell you. Don't worry, there is small difference, very small difference. So there is a very small difference between syntax tree and parse tree. This I will explain. But remember, this is an intermediate code. This is an intermediate code. Both are intermediate code. What else is an intermediate code? Can anyone tell me? SSA. Okay, static single assignment. This is also intermediate code. Anyone knows anything else? Control flow graph. Control flow graph. Okay, this is another intermediate code. Anything? Anyone knows anything else? Anything else? Okay, is there anything else that comes to your mind? Let me know. Many others, actually, there are many others possible. For example, C language itself can be used as intermediate code. This I will explain. Okay, for example, this C language, okay, this has been used as intermediate language, as intermediate code. Okay, so actually what, let me tell you, this is what happened. Okay, early C++ compiler, they generated intermediate C code. Is this clear? So actually early C++ compiler, what they did, this is what they did. Basically, you have a C++ language. Okay, so you have C++ program. Okay, now this is your source program, means this is your C++ program. Okay, and then what we do, then we have C++ compiler. This C++ compiler created C language, used intermediate this C language as intermediate language. Okay, this C++ compiler, actually the original C++ compiler, okay, it generated C language as a intermediate code. So C is a programming language. You know, C is a programming language, but it is also used as intermediate language. Okay, so this is the point. Okay, at least the original C++ compiler actually used C language as the intermediate language. So what it did? So you have a C++ program that goes through C++ compiler. Then this intermediate code will be created. Intermediate language is C language. Okay. So now you have C code. So you have C code. Now this C code goes through C compiler, and then you will get assembly language. So is this clear to everyone? What are the intermediate codes? So there are many different type of intermediate codes possible. For example, another, okay, for example, 7, 2 address code, 2 address code, 1 address code. These are also, okay, but these are not in the syllabus, so we will not study them. Okay, so 2 address code, 1 address code. So many intermediate languages, many intermediate codes are possible. Is this clear to everyone? What is an intermediate code? How many different type of intermediate codes we have? Is this clear? So for example, SSA, static single assignment. For example, quadruple, triple, indirect triple, abstract syntax tree. Okay, static single assignment, control flow graph. Okay, this is another name, but control flow graph. And you have DAG. Yes, DAG. We have already seen. We have already written this. So this is the DAG. You can notice DAG. This is also intermediate code. Okay, so I can say this is a special type of syntax tree. Actually, this DAG is a special form of syntax tree, abstract syntax tree. Okay, so this is also intermediate code. So these are the intermediate codes that we have. Okay, and what intermediate code you need, which intermediate code to choose, that depends on you. The choice, or design of an intermediate representation varies from compiler to compiler. Okay. So this is the point. Now the intermediate code can be a language. For example, I told you C language is used. Remember this intermediate language. This intermediate language, or you can say intermediate code. This either this can be a language. Either this can be a language. Either this can be a language, or this can be a data structure. Or this can be a data structure. For example, okay. For example, I can say, as I told you, C language is used sometimes, okay, in the C++ compiler. In the original C++ compiler, C language was used as the intermediate code. Okay, so for example, C language, another is 3 address code. Okay, this 3 address code, this has its own language. Okay, so this 3 address code. Some data structures are also used as intermediate language. For example, abstract syntax tree. For example, parse tree. For example, control flow graph. Okay, for example, DAG. Okay, so all these are the data structures which are used as intermediate code, and these are the languages which are used as intermediate code. So you can read this. An intermediate representation may either be an actual language or it can be a data structure. For example, C language is a programming language, but it is also used as intermediate language. Anyone has any doubts so far? Anyone has any doubts so far? Tell me. Anyone? Any doubt? Anyone? So far, everything is clear. Now, the next point I want to ask, okay, this is my next question. One compiler uses how, okay, like, can I say one compiler uses one intermediate code? Can I say this? One compiler uses one intermediate code, like many different type of intermediate codes we have. Okay, many different type of intermediate codes we have. My question is, can I say one compiler uses one type of intermediate code? One type of intermediate code. Can I say this? True or false? Can I say? Yes, Somedeep, correct. Okay, so the answer is no. The answer is not necessary. The answer is not necessary. First of all, for example, let me tell you that, okay, a compiler goes through a sequence of intermediate codes. Okay, so remember, a compiler may goes through, okay, so remember, a compiler may go through a sequence of intermediate codes. A sequence of intermediate codes. For example, let me tell you that, okay, you create parse tree, yes or no? So you can see the parse tree itself is an intermediate code. So you create parse tree, that itself is an intermediate code. Okay, so you can notice in the process, as you can see, a compiler may create a sequence of intermediate representation. For example, this is your source language. Okay, and you can see from the source language, can anyone tell me what is the first intermediate representation you create? Like, okay, can anyone tell me, like, I should not say first, but can anyone tell me what is the from the starting of the compilation phase, what comes to your mind? What is the intermediate representation that is created? Parse tree, syntax tree, yes or no? So you can notice the parse tree itself, the parse tree, or I can say syntax. There is a small difference between parse tree and syntax tree. That difference I will make clear. But you can notice from the source program, you create high-level intermediate representation. What are the high-level intermediate representation? Let me tell you. Some high-level intermediate representation are abstract syntax tree, parse tree. These are the high-level intermediate representation. And what are the low-level intermediate representation? For example, 3 address code. Okay, for example, I can say, okay, you have 3 address code, and here you have DAG also you have. Okay, so you have 3 address code, and okay, you have static single assignment. Okay, so these are the low-level intermediate code. Is this clear to everyone? So basically a sequence of intermediate codes, and okay, and near the code optimization, the control flow graph is also created. Okay, from this control flow graph is also created. So this is the point you can notice. What I want to say, that a compiler may create a sequence of intermediate code. For example, the compiler may create abstract syntax tree, 3 address code, and control flow graph. Okay, so a sequence of intermediate representations are created. and every intermediate representation has a application, has uses. Okay, different intermediate codes have different applications. This control flow graph, this is used in optimization. This is very useful in optimization. This is useful in optimization. Okay, so you can notice different intermediate representations have different uses, have different applications. So this control flow graph, this is useful in optimization. Okay, and this abstract syntax tree, this is useful in I can say this is useful in looking at the language constructs. Okay, because these are the high level intermediate representation. So if you see the parse tree, then automatically it will tell you something about the source language, how the source language, what is the syntax of the source language. Okay, so by looking at these things, okay, remember, by looking at these things, they will tell you the syntax of the source language. So that is the reason these are called high level intermediate representations. By looking at 3 address code, by looking at SSA, you can't say what is the syntax of the source language, but these will tell you the syntax of the source language also. So this is the point. Okay, so you can just read all these points. Now let's go. We have already seen what is 3 address code. Okay, in the last lecture we have already seen. So these are the points. So far everything is clear, what we have seen so far. Okay, so far these points must be clear. Remember, these points must be clear. Why intermediate code? Why intermediate code? Is this clear? Second, types of intermediate code. Types of intermediate code. Okay, so these 2 points, are they clear so far? Anyone has any doubt in these 2 points? So we have seen these 2 points. Why we need intermediate code and what are the types of intermediate code. Many different type of intermediate code we have, and a compiler, the same compiler can go through a sequence of intermediate code. Okay, you have a compiler, so your compiler can go like this. Okay, your compiler can create many different intermediate representations. It can create abstract syntax tree. Okay, and it can create I can say it can create 3 address code. It can also create control flow graph. Okay, so basically a compiler goes through a sequence of intermediate code. Okay, now the next question I want to ask. Okay, optimization we have already seen in the last 3 lectures. We have already seen. When should we perform optimization? Tell me, where should we perform optimization? Can anyone tell me? In this whole program, where should we perform optimization? Like at what point of time? Where should we perform optimization? Can anyone tell me? Okay, let's see where should we perform optimization. Let us assume that I am performing optimization here. Let us assume I am performing optimization on the abstract syntax tree. Okay, on the parse tree, I am performing the optimization. Can anyone tell me what are the pros and cons? Can anyone tell me what are the benefits if I perform optimization here on the parse tree? You have a parse tree. On the parse tree, you have a parse tree. On this parse tree, I perform optimization. What are the benefits? So if I perform optimization here, what are the benefits? If I perform optimization on the intermediate code, what are the benefits? If I perform optimization on the target code, what are the benefits? Where should I perform the optimization? So let's see. Let me tell you. If you perform optimization on abstract syntax tree, means if you perform optimization on this parse tree, if you perform the optimization here, then what are the benefits? The benefits are machine independent. Your optimization is machine independent. But your optimization is now source language dependent. Yes or no? Are you getting my point? So basically, if you perform the optimization here, then the code you are writing a code. Just think about it. Okay, you are the writer, you are the coder. Okay, so let me tell you, you are the coder. Okay, so you are the programmer. Okay, you are the coder. Okay, and you are writing optimizer. Okay, there is a optimizer code you are writing. Okay, so you are writing optimizer code. This optimizer code you are writing. And let us assume this optimizer code you are writing to optimize the abstract syntax tree. Okay, for optimization on abstract syntax tree, for optimization purpose. Okay, on abstract syntax tree. Can anyone tell me if I write this optimizer code on abstract syntax tree, and you already know that this abstract syntax tree, this is very high level. Yes or no? This is high level because this actually depends on source language. So this abstract syntax tree, this is actually high level. Okay, so it will depend on the, for example, if you have a C language, if this abstract, if you are writing this optimizer code for abstract syntax tree of C language, then what you do? Tell me. Then this code you cannot use on the Java language, yes or no? So this is the problem here. If you do optimization here on the parse tree, then benefit is machine independent. Okay, but the disadvantage is it is too high level. Okay, so basically you cannot reuse this code you cannot use on the Java language. Okay, yes or no? Next, if you do the optimization on assembly language, basically here, if you do optimization here on the assembly language, so basically here the assembly language will be created. Okay, so here you will get assembly language. Okay, so now you can notice if you do optimization on assembly language, then what is the disadvantage? Disadvantage is machine dependent. Okay, so what is the best place? The best place for optimization is intermediate language, means here. Okay, at this point of time, on the intermediate code, if you do optimization, then you can use this code optimizer. This code optimizer code you can use anywhere. So this is the benefit. On the intermediate language, if you do the optimization, then it is machine independent and also source language independent. So basically, this is the best place for optimization. But remember, this is the best place for optimization, but you can do optimization here also, here also, here also. Okay, so finally you have this picture. Okay, this picture you have. So okay, most of the optimization we perform on the intermediate code. Remember, most of the optimization, majority of the optimization we perform on the intermediate code, so that we can reuse this. Okay, but the point that I want to say is that this you will get. Okay, if you can perform optimization on any point of time. Okay, you can point optimization. Okay, so majority, I can say majority of optimization is performed here. Majority of optimization is performed on intermediate code. Okay, optimization is performed here. But remember, here also optimization can be performed. You can perform some optimization. Some optimization you can perform here also. Some optimization you can perform here also. Okay, so on the assembly language, you can perform optimization. Okay, so these are the optimization, but majority of the optimization is performed on the intermediate code. Why we perform majority of the optimization on intermediate code? Because so that we can reuse this. Okay, so that we can reuse. Majority of the optimization is performed here. Why so that reusability, again reusability, so that we can reuse this code. If we are writing a code optimizer which optimizes the intermediate code, then we can reuse this optimizer, reusability of optimizer, or I can say reusability of compiler, because anyway this is a compiler phase. Okay, so let's see, this is the question. Is this point clear to everyone? Where we can do optimization, majority of the optimization is done on the intermediate code, but you can do optimization here also, here also, here also. You can do optimization anywhere. This optimization is machine dependent. This is machine dependent optimization, and this optimization is actually machine independent. This is machine independent. Okay, so tell me, what is the answer for this GATE question? For this GATE exam question, what is the answer? Anyone? Generation of intermediate code based on abstract machine model is useful in compilers because you can notice it enhances the portability of the front end of the compiler. This we have already seen. Okay, so this question we have already seen. This will enhance the portability of the, portability means reusability, I can say. Okay, I can say reusability of the front end of the compiler. Okay, so this is the point. Next, what is the answer for this? One of the purpose of intermediate code in compiler is, what is the purpose of intermediate code? One of the, tell me. It is, see, okay, the option D is saying it is not possible to generate code for real machine directly from high level, but this is possible, right? Yes or no? This we have already seen. This is possible, right? Yes or no? This is definitely possible. I told you, without intermediate code, you can do. but you have to do, okay, see what is the option D saying. Let me tell you option D. This option D, I told you, for language L1 you have front end F1. These are the front end. Okay, so option D means without intermediate code, without intermediate code. Okay, so you have front end L1, L2, L3, L4. Okay, so these are the front end F1, F2, F3, F4. Without intermediate code also you can directly do. Yes or no? I told you yes or no. Without intermediate code you have to do this. If you don't use intermediate code, then you will have to do this. This is what you will have to do. Are you getting my point? Okay, so this is definitely possible, but if you use intermediate code, okay, then the purpose is basically to increase the readability. This you reusability. Tell me the answer here. One of the purposes, okay, so you cannot increase the chances of reusing the machine independent code optimizer. I told you portability of the optimizer. These things I told you here, you can notice here. So why we do this code optimization? These are the purpose. So you can notice here. Here I told you all these purpose I told you here. You can notice. Okay, ease of optimization and also why intermediate code, so that okay, you can say portability of optimizer is also okay. Portability of machine independent code optimizer is also increases. Portability of machine independent code optimizer increases. This we have already seen. Okay, so let's see. Okay, so here increases the chance of reusing the machine independent code optimizer in the other compilers. Okay, so this is the point. Now let's see some code optimizations. I told you that code optimization can be done on the abstract syntax tree, on the target code, or also on the intermediate code. Some code optimizations, why we perform majority of the optimization? Yes, this will be available on the YouTube. This class will be available on the YouTube. Okay, on the Go Classes YouTube channel, this class will be available. Tell me why. Okay, I told you why majority of the actually some, or I can say major. Okay, some actually I can say many. Okay, majority of the optimizations, majority of code optimizations, they are actually performed on intermediate code. Why? Majority of the code optimization are performed on intermediate code. Why? Because they will enhance the compiler, okay, to the target processor. Okay, because we can use the code optimizer. Yes or no? The reason is actually okay. Why? Okay, because the reason is actually reusability of, so that we can reuse. Okay, reusability of this type of this optimizer reusability of optimizer which does optimization on intermediate code, which does optimization. Okay, what about option B? Program analysis is more accurate on intermediate code than on machine code. This is not true. Okay, program analysis is actually much more accurate on the assembly language code. Okay, the machine code means assembly language code. On the assembly language code, actually you can do better optimization. Okay, because why you can do better optimization? Tell me. On the machine code you can do better optimization. Why? This is not true. This is not true. Why this is not true? Tell me. Because on the machine code you can do better optimization. The better improvement, better optimization means better improvement. Okay, if you okay, optimization means improvement. See, optimization means improvement. You already know optimization simply means improvement. Now what I want to say is that on machine code you can do better improvement. Okay, on machine code, if you do on machine code you can do better improvement. You can do better improvement. Why? Because now, why you can do better improvement? Because now you know what are the machine registers and all many other things you have. Yes or no? It will use the registers available on the machine. Correct. That is the correct. Basically, we can do better improvement because now we have knowledge of machine. Because of knowledge of target machine. Yes or no? Is this clear? Because now you have knowledge of target machine, so you can do better improvement. More accurate improvement you can do. Better improvement basically means more accurate improvement you can do. More accurate optimization you can do on the machine code. Because now you have the knowledge of the target machine. See, when you are doing the optimization on the intermediate code, on intermediate language, let me tell you, the optimization is easy. The optimization is easy. And optimization we do here on intermediate language, we do optimization. The reason is so that we can reuse. But remember, here we don't have knowledge of target machine. We don't have, yes or no? Here we don't have knowledge of target machine. Info of target machine. Is this clear to everyone? Anyone has any doubt in this? Okay, so this is the point. So this B is not true. The information from data flow analysis cannot otherwise be used for optimization. These are not true, as you will see. Okay, as you will see, these things are not true, because even if you don't have intermediate code, now also you can do optimization. In the class, in the beginning of the class, I told you, you can notice here. See, even if you don't have intermediate code, let us assume you don't have here, you can notice here, you don't have intermediate code, still you can write the optimizer. Okay, now you have to write the optimizer for everything. Yes or no? You have to write optimizer for this. You have to write optimizer for different. Basically, you cannot reuse the optimizer. This is the point. Yes or no? Basically, here I can say cannot reuse. Here you cannot reuse optimizer. Okay, but we can optimize. Okay, for every machine and source language combination, we have to write optimizer. Yes or no? For every, I can say here, for every source language, okay, for every source language, machine combination, we have to write optimizer. Yes or no? We have to write a separate optimizer. We have to write a separate optimizer. Is this clear? All these points, are they clear to everyone? Why some option is correct, why some option is not correct? All these points, are they clear? Okay. So I hope these questions are clear. Tell me, what is the answer for this GATE 2021 question? For this GATE 2021 question, what is the answer? In context of compiler, which of the following is not an intermediate representation of source program? So 3 address code is there, abstract syntax tree, control flow graph. The answer is symbol table. And let me tell you, and I also told you, same compiler can use all these three. Actually, same compiler uses all these three. You have a same compiler that will create abstract syntax tree, that will also create 3 address code, okay, and that will also create control flow graph. This control flow graph is created why? Because this is useful in optimization. This is useful in code optimization. Okay, is this clear to everyone? So same compiler can go through, same compiler can use many different intermediate representation. So same compiler uses all these three. Yes or no? Is this clear? All these three are used by the same compiler. It will go through a sequence of intermediate codes. Okay. Now, So what we have seen so far, actually, in the last three lectures, we have seen three address code. This we have seen. We have seen all the 3 points, quadruple. Okay. So these things we have seen, quadruple we have seen, triple we have seen, indirect triple we have seen. In the last three lectures, we have seen all these things. Okay. We have also seen static single assignment. This also we have seen. Control flow graph. This is also we have seen. What we have to see? We have to see abstract syntax tree. We have to see what is a DAG. Okay. So these two we have to see. So let's start with the abstract syntax tree. So first we will study abstract syntax tree. Symbol table is part of compiler. Yes, symbol table is part of compiler because symbol table is used to to store the information, and that information is used by the different phases of the compiler. But symbol table is a data structure which is not an intermediate code. Symbol table is used to store the information so that different phases can use that information, okay, for the compilation purpose. But symbol table is not a intermediate representation. Symbol table is not an intermediate code. Okay. Is this clear? Is this clear? In all the phases it is used. The symbol table is used in all the phases. Every phase uses the symbol table. Okay. If you are a Go classes student, then it is already taught by the Sachin. Okay. Sachin has already taught that where symbol table is used. In all the phases, every phase can use symbol table. This has already been taught. Okay. Is this clear? Okay. So if you are a Go classes student, then these things have already been taught. Okay. Symbol table, implementation of symbol table and all these things, where symbol table is used and all these things. Okay. Now let's see what is the abstract syntax tree. So let's study this. What is the difference between abstract syntax tree and what is the difference between parse tree? So let me tell you. First of all, remember abstract syntax tree. Abstract syntax tree. First of all, what is abstract syntax tree? Another name is, by default, this is also known as abstract syntax tree. This simply means syntax tree. So we will not, okay, syntax tree. In short, it is called AST. And this parse tree is actually concrete syntax tree. Concrete syntax tree. Concrete syntax tree means your parse tree. Now tell me, can anyone tell me what is the difference between parse tree and syntax this tree? Okay, for example, if you have this expression, let me give you some expression. Okay, consider this expression x equal to y plus z. Can anyone create abstract syntax tree for this? Abstract syntax tree. Okay, I will tell you how to create abstract syntax tree. I will tell you, don't worry. But actually the abstract syntax tree is created like this. Okay. For this expression, the abstract syntax tree, how this is created? Can anyone tell me? For this expression? Okay, let's take some expression. Okay, so let's see how to create syntax abstract syntax tree for this. So let me tell you, okay, don't worry about it. I will explain how to create, but let me tell you, this is how it is created. So first of all, you have equal. Okay, so this is your, I can say this is your language construct. Yes or no? This is a part of the language. Yes or no? Tell me yes or no. This is a part of language. This is not a part of language. This is operand. I can say this is not part of the language. I can say this is the language construct. This is called language construct. This is called language construct. Okay, so basically it's like this. This is the operator. This is the operator. So in the abstract syntax tree, the operator is the, okay, so here you have x and here you have y plus z. Here you have abstract syntax tree of y plus z. Okay, now how to create abstract syntax tree for y plus z? How to create this abstract syntax tree for y plus z? That is created like this, plus y and z. So this is how we create abstract syntax tree for this expression. Okay, can anyone tell me how to create parse tree? Just tell me this point. How to create parse tree for this expression? Tell me. What you need to create parse tree? Can anyone tell me? If you can answer this question, then you will automatically know the difference between abstract syntax tree and parse tree. abstract syntax tree and parse tree. What is the difference between these two? That you will automatically know if you can answer this question. What we need? Grammar. Yes, very good, very excellent. So we need grammar to create parse tree. So that is the point. Okay. So this is the difference between abstract syntax tree and parse tree. We cannot create parse tree for this if we don't have grammar. So here we need grammar. If you want to create, okay, then you need grammar. Okay, and let us assume you already know the grammar. Then something like this will happen. Expression will go. Okay, in expression will go to, I can say, term. Okay, term, operator, term, something like this. Yes or no? Okay, I can say expression can go to expression, operation, expression. This is the okay. Next expression can go to term. Expression can go to term. Term can go to identifier. Identifier can go to X. Operator can go to equal. Expression can go to expression, okay, operator and expression. Then again, this will go to term. Then this will go to identifier. This will go to Y. This will go to plus. This will go to. Can you see the difference? Just tell me this point. Can you see the difference between abstract syntax tree and parse tree? Your parse tree needs grammar. Let us assume you already know the grammar. Let us assume your grammar is this. For example, let us assume you have grammar is this. Okay, let's assume your grammar is this, that expression can go to expression, operation, expression, and expression can also go to term. And you can see, okay, term can go to identifier, something like this. Okay, something like this. Okay, if you have this type of grammar, then this will be your parse tree. This will be your parse tree, and this will be your abstract syntax tree. So is the difference clear? Clear? What is the difference between parse tree and abstract syntax tree? Is the difference clear? Tell me. Is this difference clear? So remember, the difference is very small difference we have. Okay, and the difference is like this. For example, if you create the abstract syntax tree for this, so what will be the abstract syntax tree for this? I told you operator. Let us assume, okay, let us assume you do from left to right. Okay, let us assume that the associativity is from left to right. Then how you will create abstract syntax tree? The abstract syntax tree will be created like this. Okay, so first you will do this, correct? Yes or no? If, okay, let's assume left associativity is from left to right. Okay, then what will happen? First you will do this, then you will do this. What it means? It means plus, okay, 2, and here you have 9 minus 5. Okay, so 9 minus 5 can be written like this. So this will be, yes or no? So this will be your abstract syntax tree. Is this clear to everyone? So in the abstract syntax tree, I can say the nodes are basically language constructs. Okay, so remember, and how the parse tree will look like? For this expression, how the parse tree will look like? The parse tree, again, it will depend on the grammar. Okay, so the parse tree will be like this: expression going to expression, operation, expression, and this expression will go to term, this will go to identifier, this will go to 9, this will go to minus, this will go to expression, something like this. Okay, so okay, so this will go to plus, and I think this will go to expression. So something like this. Okay, this will go to expression, operation, expression, something. Okay, are you getting me this point? Is this clear? Is the difference clear? What is happening here? Term, identifier, and then 9. Okay, and this minus, and this term, identifier, and this is 5, and this plus, and this term, identifier, and then 2. So the difference between abstract syntax tree and, okay, and the parse tree, the difference is clear, I think. Yes or no? So the difference is very simple, that the, okay, what is the difference? Are they same? Are abstract syntax tree and parse tree, they are different? Yes, they are different. And the difference is that parse tree is also called okay, this parse tree, the another name for parse tree is actually, you can say, so this is the difference actually. In parse tree, the interior nodes are the non-terminals of the grammar. This depends on the grammar. Yes or no? This depends on grammar. So this is the point. Okay, so this is so this is the explanation. Okay, now how to create abstract syntax tree? I told you. Okay, in the abstract syntax tree, how to create? Okay, in the abstract syntax tree, the internal node, the internal node is a language construct. Let me tell you, the internal node is actually language construct. What do I mean by language construct? Language construct, for example, operator, for example, operator, okay, for example, keyword, for example, keyword, for example, keyword. So these things, okay, language construct, these are the internal nodes. So internal node will be a language construct. And what is the external node? What is the external node? Okay, so here you can see the internal node is actually the language construct, and the external node, okay, while the children is actually some meaningful component, I can say, okay, some meaningful component. For example, your identifiers, okay, your actual values, I can say, your actual values. Okay, so this is your abstract syntax tree. For example, if you have this, how will you create abstract syntax tree for this? Can anyone tell me? How will you create, okay, how will you create abstract syntax tree for this statement? For this statement, anyone? Tell me, anyone? For this, how will you create abstract syntax tree? So this will become your internal node. Okay, as I told you, internal node is basically language construct. Okay, language construct. Okay, so the operator, keyword, these are the internal nodes. So this will become the internal node. This will become left child, and this will become right child. Yes or no? So something like this you will get. Okay, so here what will happen? Here this will happen. Okay, so you have while, and for this while there will be two children. One will be expression, another will be state. Okay, is this clear? Is this clear? How to create? Actually, in the GATE exam, they will only ask you how to create abstract syntax tree for the expression. How to create abstract syntax tree AST for expression. They will ask you only this. Okay, but anyway, I am just telling you how to create abstract syntax tree if you have any type of statement. Actually, okay, but remember, in the GATE exam, they will only ask you about the expression. Okay, so for example, if you have some expression, then how to create? How to create abstract syntax tree for this? For this will be the abstract syntax tree. Yes or no? Is this clear to everyone? So for example, you have this. Okay, see, a plus, what you have, a plus a multiplied by b minus c plus b minus c multiplied by d. Okay, so how will you create abstract syntax tree? Okay, so how will you create abstract syntax tree for this? So for this, abstract syntax tree will be created like this. Okay, what you will do? Okay, so what you will do here? Okay, so here what you will do, very simple. So this is what you are going to do. So for example, you have a plus, okay, so this is what you will do. First you can see b, c, and then you will do b minus c. So this b minus c is done. Okay, then you will multiply this with a. So you will multiply this with a, correct? And then what you will do? So just multiply this with a, and then what you do? Then you add this to a. Okay, so then you add this to a, and then what you do? Then you create, okay, b, c, and then you b minus c, and then with d you multiply, and then what you do? Then you add this to this. This is how you will create abstract syntax tree for this. So this is your abstract syntax tree. Is this clear to everyone? Is this clear? In the abstract syntax tree, Ananya, we create node for everything basically. Okay, b minus c is common. I will tell you, there is something called DAG, a special type of abstract syntax tree, that is called DAG. Okay, that I will teach you, but right now the abstract syntax tree is very simple. Is this clear? How to create abstract syntax tree? Remember, anytime you have this type of thing, expression, operation, expression, if you have this, then what will be your abstract syntax tree? That will be operation, expression 1, expression 2. If you have expression 1, expression 2, so this is your abstract syntax tree. Okay, is this clear? Anyone has any doubt in this? Can anyone tell me? Okay, can anyone tell me one interesting question I want to ask. Okay, maybe I don't know whether you are wondering this or not. I told you that syntax tree, that abstract syntax tree means syntax tree. Okay, both are same thing. But parse tree is called concrete syntax tree. See, parse tree, that is called concrete syntax tree. This is called concrete syntax tree. We call it concrete syntax tree. Concrete. Okay, concrete. And this syntax tree we call it abstract syntax tree. Why? Can anyone tell me? Okay, can anyone tell me? I mean, what is the? I want to know the difference between these two words. What is the difference? Like why this is called concrete and why this is called abstract? What is abstract here? What is abstract here? Tree is abstract or syntax is abstract? What is abstract here? What is concrete here? Syntax is concrete or tree is concrete? Tree is concrete or syntax? Syntax is concrete. Here syntax is concrete. Here syntax is concrete, and here syntax is abstract. What that means? Can anyone tell me what that actually means? Let me tell you. Let me tell you. Are you wondering that, okay, for example, okay, let me tell you, the answer is very simple. The abstract syntax tree actually does not bother about every single detail. Okay, this abstract syntax tree is very abstract actually. Okay, this abstract syntax tree, this does not worry about every single detail of the expression. Okay, so basically this just gives you, I can say, this will just tell you how things are happening. Okay, so this will tell you only the behavior. Yes or no? This will only tell you what is actually happening. This will only tell you semantics, I can say. This will only take care of the semantics. Okay, so deals with the semantics. Deals, I can say, okay, basically this will tell you the semantics. Okay, this only bothers about semantics, I can say. Bothers about what is actually happening. For example, if you have this expression, okay, 9 plus 5 minus 2. If you have this expression, let us assume this is your expression. Now, abstract syntax tree does not worry about these parentheses. Some student was asking what happens to these parentheses. Abstract syntax tree does not worry about these parentheses and all. Okay, is this clear? So abstract syntax tree only does this. That's it. You can see your this parentheses are gone. Yes or no? These are gone. These are not in abstract syntax tree. Yes or no? Is this clear to everyone? So basically, abstract syntax tree means, so that is the reason I am saying that here syntax is abstract. Syntax is not concrete. Syntax is abstract syntax. Yes or no? But in the parse tree, what will happen? For this, if you make the parse tree, then what will happen? If you make the parse tree, then parse tree will take care of parentheses also. Yes or no? Your grammar will take care of parentheses also. Correct or not? Is this clear to everyone? So here something like this will happen. Expression goes to expression, operation, expression. Something like this will happen. And this expression again will go to expression, operation, expression, something like this. Or maybe, okay, bracket, sorry. Here what will happen? This expression will go to bracket, expression, and close bracket. Now this expression will go to expression, operation, expression. Now this operation will go to plus, this operation will go to minus, this will go to okay, term, identifier, and 2. And this will go to term, identifier, and 5. And this will go to term, identifier, and 9. So can you see this? Can you see this? Not this. Okay, focus on this point. Focus on this. So can you see that parse tree is basically, that is the reason this is called concrete. That is the reason this is called concrete syntax. This is concrete syntax tree. It actually deals with the syntax actually. Okay, but it does not bother about small things, I can say. Okay, doesn't bother about small detail. Yes or no? Is this clear? Anyone has any doubt why this is called abstract syntax tree and why parse tree is called concrete? So that is the reason this parse tree is called concrete syntax tree. Okay. So anyway, like this, you can do. Now in the GATE exam, they will not ask you abstract syntax tree and parse tree for block. Remember, so far what we have seen, can anyone tell me? So far what we have seen? So far we have seen abstract syntax tree for expression. Yes or no? So far what we have seen? We have seen abstract syntax tree for expression. For expression. This is what we have seen. But remember, abstract syntax tree can be created for any basic block. For basic block also it can be created. Abstract syntax tree can be created for whole program. Because remember, abstract syntax tree is an intermediate representation. This is an intermediate representation. This is a high level intermediate representation, I can say. High level intermediate representation. So you can create abstract syntax tree for the whole program. You can also create for the basic block, but we will not study this. Okay, so skip. Basically these things you can skip. No one will ask you, don't worry. No one is going to ask you these things. Okay, so basically this is important, abstract syntax tree for expression. But the point is this, you can create abstract syntax tree for basic block also. You can create abstract syntax tree for whole program also. Okay, for example, if you have this basic block, this is a basic block. For this basic block, this will be the parse tree. Okay, but for this basic block, what will be the abstract syntax tree? So this is a block, you can notice. Okay, in this block, what you have? X equal to 42. So this is a block, you can notice. Here you have X equal to 42. And what you have? You have Y equal to X divided by Y equal to X divided by 7. Okay, so something, this. Now this is your block. Now for this block, what will be the abstract syntax tree? So this is very simple, because you are writing. So for this block, then this is how you can write. Okay, this you have a block. Now in this block, you have two things. Okay, in this block, you can notice you have this statement, this statement. So in this block, you have a sequence of statement. So here you have, so you will create abstract syntax tree for this. For this abstract syntax tree will be this. And you will create abstract syntax tree for this. Okay, so for this abstract syntax tree will be this. Okay, so you can notice Y and then division and then X and then 7. Is this clear to everyone? That we can create abstract syntax tree for expression, we have already seen. We can create abstract syntax tree for basic block, and we can also create abstract syntax tree for the whole program. Okay, so for this basic block, if you have this basic block, then for this basic block, this is the abstract syntax tree. For this block, if this block is B1, then this will be block B. Is this clear? Anyone has any doubt? These are the nodes. These are the nodes. This is a node. This is a node. This is a node. This is your abstract syntax tree. Okay, so don't worry, they will not ask you these things, but I just wanted to tell you, this is what I want to tell you, that abstract syntax tree or simple syntax tree is created for whole program by the computer, but we will only focus on abstract syntax tree for single assignment. For example, this is a program. For this program, this will be the abstract syntax tree. Don't worry about it, how it coming, don't worry, just skip this. But I just want to tell you that for this program, for this whole program, this will be the abstract syntax tree. This is the abstract syntax tree for previous program. Okay, but remember, skip how it is created. Skip how it came. Don't worry about how it came. Is this clear? Okay, so this is your abstract syntax tree. Now we can move forward. Okay, now we will study directed acyclic graph. Okay, so we will take a break, and after the break we will study directed acyclic graph. Okay, so this directed acyclic graph, this is a variant of syntax tree. This is a special type of syntax tree. Okay, so remember, this is the next topic. Our next topic will be directed acyclic graph. Directed acyclic graph. This is a variant of, this is a variation, or I can say this is a variant of abstract syntax tree. Or I can say this is a special type of syntax tree. So let's see, directed acyclic graph. I told you that directed acyclic graph is actually a variant of syntax tree. In this directed acyclic graph, we don't recompute any already computed expression. Okay, so that is the difference between syntax tree and directed acyclic graph. Okay, so basically, if you have already computed some expression, we will not compute it again. So let me tell you the difference between directed acyclic graph and abstract syntax tree. First, let's see the difference. Okay. So you can notice here this expression we have. Okay, for this expression, let us see what will be the. So you can notice for this expression, this is the abstract syntax tree. Now for the same expression, what will be the DAG, directed acyclic graph. Okay, so this A plus A into B minus C, A into B minus C. Okay, and then what we have B minus C into D. Okay, so this is the expression we have. For this expression, you already know what is the abstract syntax tree. Abstract syntax tree is very simple. That okay, so you have B, you have C, you will compute B minus C. Okay, so this B minus C you are computing, then you are multiplying with A. Okay, and then what you are doing, you are adding with A. Okay, then you are adding with A, and then what you are doing, you are again computing B minus C. So this is B, this is C, and you are again computing B minus C. Then again you are multiplying with D. So this you are multiplying with D. Okay, and then what you are doing, then you are doing the addition. So you can notice one thing. What here, what are the things to notice? First of all, you can notice that this we have already computed. Here we have computed B minus C basically. Okay, this what this means? This means B minus C. So here you have already computed. This means B minus C. Here also we have B minus C. So this same expression we are computing two times. Okay, again and again we are computing this. Okay, so you can notice the same expression we are computing two times. Okay, so this is what we do in abstract syntax tree. But there is something called DAG, directed acyclic graph. This in this representation we don't compute anything twice. Okay, if we have already computed something, we will not compute it again. Okay, so what we are going to do? So this expression. So okay, again what you will do? Just go from left to right. Okay, just go from left to right. This expression, this is your A. Okay, now this is your A plus this. So basically this A plus this. Okay, this we have to compute. So first we have to compute B minus C. So what you will do, you have B, you have C, you will compute B minus C. Okay, so here you have computed B minus C. Okay, so you have already computed B minus C. I can say that here at this point of time you have computed B minus C. Then what you will do, you will multiply with A. You will multiply with A. There is no problem. Everything is good, no problem. Now this is over. Now you can notice, okay, what you will do here, B minus C into D. Here what you will do, see B minus C you have already computed. This is B minus C. Okay, this is your B minus C. Okay, so now what you can do, you can multiply this. This you have to multiply with D. Okay, so you can multiply this. This you can this is B minus C. This you can multiply with D. Okay, now this is also over. This is also over. Now you have to add. Okay, so let's assume. So first we add these two. Okay, then what you have to do? So this is your A into B minus C. Remember, this is your A into B minus C. In this you have to add. Okay, in this you have to add A. Okay, so A you already have. You don't have to create another node for A. Don't create. Okay, so these are the differences. Okay, remember, don't create another node for A. Don't create. Okay, just you use this and use this and add them. Okay, so now you have added these two. These two you have added. Now what you will do? Now you will add this with this. So this is your DAG. Is this clear to everyone? In the DAG, we don't create any node if we already have such node. So if you have already computed something, you don't compute it again. Don't create new node for the same thing. For the same thing, don't create new node. So this is the difference. This is the major difference. Okay, you can notice these are the same things. Oh, this and these are the same things. So you can note these are the same things and these are the same things. Don't create new node for the same things. So this is your DAG. So this is the difference between DAG and abstract syntax tree. Is this difference clear to everyone? So basically in this DAG, what we do in this DAG, the idea is very simple. What is the idea? Okay, don't create a node for the same. Don't create different node for the same thing. Don't create different node for same thing. Okay, basically don't recompute the same. Okay, the same expression don't recompute. Okay, don't recompute same expression. So this is the idea of DAG, directed acyclic graph. Okay, so can anyone tell me one point I want to ask, how can you implement such a thing? Okay, this directed acyclic graph, how can you implement? Like, okay, you have to remember, right? Yes or no? Okay, as you are going, you have to remember. Am I right or no? Here at the, okay, this example you can take. In this example, how did we create? Okay, here you are creating, for example, okay, just tell me this point. This point I want to ask. A plus A multiplied by B minus C. Okay, plus B minus C multiplied by D. Okay, just tell me this point. When you are creating DAG, okay, then how a computer will do implementation? How a computer will do? Tell me. Actual implementation. Tell me. Can anyone tell me? Okay, like how the implementation will know that you have already computed B minus C? How you will know? Tell me how you will know whether you have already computed B minus C. Can anyone tell me? How the implementation, how the compiler, how the computer will know? How the compiler will know that you have already created, you have already computed B minus C? Anyone? Just remember it. Yes or no? Just remember what you have computed. Remember? Yes. Yes, yes. Very good. Very good. HP, very good. We will store in some data structure. Very good. Okay. Basically, this is what we are going to do. See what we are going to do. You are computing B minus C. Okay. So first of all, you can notice, okay, for A, we have a node. Okay. So, okay, just go from left to right. Okay. Let's go from left to right. Let's go. Okay. Let's go from left to right. Now, what you will do? Very simple. First, you have A. So you will remember that you have A. And this is identifier. Okay. So you will remember that there is identifier A. Okay. So this is A. Next, what you will do? This plus. So, okay. So next you have A. But A you already have. A you already have. Yes or no? See, in the implementation, you are already stored A. So don't create another new node for A, because you will go and check. Go and check this. You already have a node for A. So don't create another node for A. Okay. Next, we don't have to do this. Actually, we will have to, because multiplication has more priority. Yes or no? This multiplication has more priority. So what you will do? First, you have to calculate BC. So you have B and you have C. Okay. So you have B, you have C. So first, what you will do? You will compute B minus C. Okay. So this is what you have done. Okay. So you have minus. Okay. So this is your data structure, minus, and this is B. Let me write like this. Okay. So let me just write like this. Let me give it index. So this is array. Actually, this is array. Actually, okay. This is some data structure. Let's assume this is array. Let's assume this is array. Okay. So because this is array, so we have index. Okay. So let's assume this is the index 1, index 2, index 3, index 4, like this. Okay. So what you will do here on the index 4, what you will do on the index 4, you will write this, that okay, the operator is minus and B comma C, but B comma C means 2 comma 3. Yes or no? Means yes or no? Index. I am writing the index. Means this expression, this expression. Don't create new node for this expression. So B minus C. So this is the operator. This is the left operator. This is the right operator. So remember, this is the operator. This is the operator. This is the left operator. This is the left operator. And this is the right operator. Okay. So like this. Now you cannot, and this is the index. This is the index. Array index, I can say. Okay. So now you can notice. So now you have stored that B minus C. Don't calculate it again. Okay. So you have already calculated B minus C. Now what you have to do? Now this expression you have calculated. Now you will do. Okay. Now you will do this. Have we calculated this? Tell me. Have we already calculated this? Have we calculated this? No, we did not calculate, because in here you can notice we did not calculate. So calculate it. Okay. So let's calculate it. Okay. So because we did not calculate. So what you will write here? Tell me, what are the entries? Tell me, what are the entries? Tell me, what are the entries? This is the index. This is the operator. What are the entries? Anyone? What are the entries here? Here 1 and here 4. 1 comma 4. Yes, very good. Excellent. Okay, 1 comma 4. Now what we do? Now we need to do this. But you already have calculated A. So now this we have not calculated. This we have not calculated. So what you need to do? you need to do plus and this. What is the next entry? Tell me the entry. Tell me the entry. The entry is this. Okay, 1 comma 5. This is the entry. Operator is plus 1 and 5. Very good, excellent. Okay, now what we need to calculate? Now we need to calculate. So this we have done, this is done. Okay, now we have to calculate this. Then first we have to calculate b minus c. B minus c is already computed. Go check in your table. Go and check in your table. In your table, b minus c is already calculated. So this is already calculated. This is here. This is b minus c. So you have already calculated. Now you will multiply with d. Multiply with d. What will be the entry? Tell me the entry. Just tell me the entry. I am interested in the entry. What will be the entry? Entry will be 7. Operator is multiplication. Operator is multiplication. Operator is multiplication. B minus c means 4 and d means d. Okay, we have to create entry for d. Okay, we have to create entry for d. We have to create entry for d. Identifier d. We have to create entry for d, and then we have to create that multiplication is the operator. Then 4 comma 7. We have to create entry for d. Yes or no? Yes or no? We have to create entry for d. For this we have to create entry. Okay, so this is how you can do. Next, what you have to do? Next, very simple. Next, this will be plus. So next entry will be plus. Okay, this will be the next plus 58. Yes or no? The last entry will be plus 58. Okay, so the last entry will be actually plus 58. I hope this is clear to everyone. I hope this is clear that this is your DAG and this is actual implementation. This is how your compiler will implement. Is this clear? Anyone has any doubt in this? How your compiler will create DAG? How your compiler is going to create DAG? Is this clear? Okay. So you can notice this is your DAG and how the compiler will create DAG. I hope that point is clear. So you can notice here the DAG are stored in array of records. Every record is a node. Okay, first of all, okay, DAG, these are stored in array of records. Each record is a node. Remember, array of records. Each record is a node in array. I can say record in array. That simply means node in DAG. Okay, so okay, for example, this is your DAG. Just take this DAG. Okay, take this expression. What is this expression? What this expression is doing? This is doing I equal to I plus 10. Last entry plus 6 8. Okay, so here what is the last entry? You can check it out. Rasi, maybe I have made some mistake. Maybe you can check it out. Let me check it out. Here have I done some mistake? Here where is this? Okay, the last entry will be actually, so this plus 6 8. Yes, that will be plus 6 8. This will be the last entry. Plus 6 8. Plus 6 8. This will be the last entry. Okay, is this clear? This is how we implement DAG. DAG. This is the implementation of DAG. Ananya, this is how we implement DAG. This is how your compiler will create DAG. DAG. Your compiler is going to create DAG, and this is how your compiler is going to create DAG. No, this is the implementation of DAG. Your compiler will create DAG. Okay, so how your compiler will actually, this is what we can see. We can see this. Okay, but compiler does not understand this. Compiler will actually, this is the implementation. I can say this is the actual implementation. This is how your compiler will do. This is how your compiler is going to do. Okay, there can be some different implementation. There can be some different implementation. This is the implementation of DAG. Now, for example, this is your I equal to I plus 10. Okay, so how you will do this? Very simple. Very simple. What you will do this here? So this is your I. Okay, so first you will create, okay, this is your 10, and then you will add both of them, and then what you will do? You will assign. Then what you will do? You will assign. Correct? So this is the DAG. This is the DAG, and this is the implementation of DAG. This is the implementation. Okay, in the implementation, what will happen? This is going to happen. See, you will create okay ID identifier. So okay, this is how you are going to create. Okay, so there is identifier, and that identifier is I. Okay, then what you are going to do? Then 10. Okay, that there is a number constant, and that number is 10. So you have created node for this. You have created node for this. Now what you do? Okay, this is the index. Okay, this is the index. This is the array index. Let me write it. Index. This is 1 2 3. Now what you are going to do? So you are going to do plus. Okay, so the next entry is plus, and then plus 1 comma 2. Okay, plus of 1 comma 2, and then the next entry will be equal. Okay, so the next operator is actually equal, and that is 1 comma 3, like this. So this is the actual implementation of DAG. Anyway, so very simply you can do this. Okay, let's create DAG. This is Ullman question. Okay, so this is the question from Ullman exercise. Let's create DAG for this. Can anyone try? Create DAG for this. How many node and how many edges? Number of nodes and number of edges. Tell me. Number of nodes, comma, number of edges. Tell me, quickly tell me. Create DAG for this. How many nodes and how many edges? So this is expression, this plus this. This is the point. Okay, create DAG for this. How many nodes, how many edges? Take 1 minute. Try this. Tell me. So what is the answer? Okay, let me see. Okay, so first of all, you have x plus y minus. Okay, so you have x plus y into x minus y. So basically, first you have x plus. Okay, so this is your x, this is your y. So you calculate x plus y. This is your x plus y. This we have calculated, or I can say that this we have calculated. Okay, so this we have done. Okay, now we have done this. Now what we need to do? X plus y into x minus y. Okay, so this is your x plus y. Now we need to do x minus y also. So this is your x minus y. Don't create new node for x comma y. Don't create new node for x comma y. Okay, yes or no? Because you already have entry for x. You already have. See, you have entry for x. Okay, there is entry for x. There is entry for y. Okay, so there is entry for x. There is entry for y. There is entry for x plus y. Now you have to create entry for x minus y. Now there is entry for x minus y. So you don't create new node. Okay, so basically x minus y will be like this. Very simple. Now you have done. Now you have to do multiplication. Now you have to do multiplication. So this expression also we have calculated. X plus y multiplied by x minus y. For this also we have entry. This expression we see. This expression calculated. This expression calculated. This expression calculated. So these are the expressions that we have calculated. Okay. Now what you need to do? Now you have to add plus. Okay. Now in this expression, we have to this expression we have to subtract from this expression. See, this expression we have already created. This expression we have already created. So you don't have to create this expression. This expression you don't have to create. We have already created. Now from this expression, you have to remove this expression. Okay. So basically, this is your x plus y. From this expression, you have to remove this expression. Okay. So now what we have done? We have done x plus y minus x plus y multiplied by x minus y. This also we have calculated. Okay. Now what you have to do? This we have already calculated. This we already have. This expression we already have. So what we have to do? We have to just add this expression to this expression. See, we have this expression. We have this expression. We have this expression. Both these expressions we have. All we have to do is just add these two. this expression and this expression. These two expressions we have to add. So this is the answer. Anyone has any doubt where you make the mistake? Tell me, where did you make the mistake? So 1 2 3 4 5 6 7. So basically 7 nodes we need. Okay, and 1 2 3 4 5 6 7 1 2 3 4 5 6 7 8 9 10. So 10 edges. Anyone tell me where did you make the mistake? So 10 edges, 7 nodes. Most of the students have given correct answer. Okay, so this is the answer. Is this clear to everyone? So okay, see, let me tell you one thing. Okay, very important thing. See, don't make the wrong answer. Okay, just write what you have computed. Okay, you can write side by side. If you are confused, if you are confused, just write side by side what you have computed, what expression you have already computed. Okay, just write side by side. This is how you can do. So tell me the answer for this. This is also Ullman exercise. Tell me the answer for option A. Tell me. A plus B plus A plus B. A plus B plus A plus B. Remember, plus assume, okay, associates from left. Assuming plus associates from left. So means associativity of plus is left or right. Basically, what this means, okay, what this statement means. This statement means that if you want to do this, then this is simply, first you do this, then you do this. This is the statement. This is the meaning. Okay, so what is the answer here? Very simple. Okay, you create node for A. Okay, so side by side I'm writing. Okay, already computed nodes. Basically, I'm here writing computed nodes. Computed nodes. Okay, computed expressions. Computed expressions. Here I'm writing. Or I can say nodes in DAG. Okay, in DAG. Or I can say records in array. Records in array implementation. In array implementation. Okay, so what are the nodes? So for example, this is a node. Okay, so this you have computed. Okay, there is a node for A, there is a node for B, and now what you do? A plus B. So now you have computed this expression A plus B. Now what you need to do? So you have computed this expression A plus. So this is okay. This you have computed. A plus B. This you have computed. Okay. Now this is all also computed. Now this is all automatically done. This is automatically done. Okay. Now what you have to do? A plus B plus A plus B. So this is already A plus B. A plus B plus A plus B. So this is how you will do. Anyone has any doubt in this? So basically 4 nodes and 4 edges. Anyone has any doubt in this? Any doubt, anyone? See, you have already computed A plus B, right? Are you getting my point? A plus B. So this is your A plus B plus A plus B. And the question is saying that plus is question given. This is given to you. See, this is given to you. What is given to you? Plus is left associative. Left associative. So what this means? What this means? This means this is same as A plus B plus A plus B. Okay. So this is the point. This is the point. Yes or no? This is given. Plus is left associative. This is given in the question. Plus is left associative. What left associative means? X plus Y plus Z. What this means? This means X plus Y plus Z. Yes or no? Is this clear to everyone? Is this clear? Anyone? This is already given. Okay, so that is the reason we are doing this. Yes or no? So this expression basically this and this both are same because it is given that plus is left associative. Now very simple. Now you do A plus B, and then this you have done, this you have done. Then you just add plus. Then just add this to this. Yes. Yes. Samarpita, yes. Okay. So tell me the answer for this. A plus B plus A plus B. Okay. Tell me the answer for this question. A plus B plus A plus B. Tell me the answer. How many nodes and how many edges? So here you write already computed expressions. Here you can write already computed expressions. Okay, remember, because left associate is already given. Hello, Mr. O. Left associate is already given. Read the question. Assuming plus is associative from the left. This is already given in the question. What it means? It means that x plus y plus z, this should be computed like this. X plus y should be first, then plus z. Given, this is given in the question. Look at the question. Is this clear? For example, see, plus is left associative. Given, this is given. This is given that plus is a left associative. Plus is left associative. This is given. This is given. So what it means? It means a plus b plus a plus b. This simply means a plus b. First you do this. Okay, first you do this a plus b. Then you do this. Then you do this. And then you do this. Is this clear to everyone? Tell me. Is this clear? So this is your point. Okay, now what you will do? Very simple. You have a node for A, node for B. So you have A, you have B. Then you will do A plus B. So first we need to do A plus B. Now you have A plus B. Now what you need to do? We need to do A plus B plus A. We need to do A plus B plus A. We need to do A plus B plus A. Okay, we have A plus B, we have A. We need to do A plus B plus A. Now we need to do, so now we have A plus B plus A. This we have. Now we need to do this plus B. Okay, now what we have to do? This plus B. This plus B. Is this clear? Is this clear to everyone? So how many nodes we have? 5 nodes. I can say 5 nodes. And how many edges? 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 6 edges, right? So we have 5 nodes and 6 edges. Is this clear to everyone? Because in the question it is given that plus is left associative. Next, option C. What is the answer for option C? A plus A. What is the answer for this option C? Tell me. For option C. This is the expression. A plus A plus bracket is given. A plus A plus A plus bracket is given. A plus A plus A plus. Okay, so this is the question. So again, this is a very easy thing. Here you write already computed expression. Okay, just write here computed expression, so that you don't get confused. Computed expression. So compute A. So first we compute A. Okay, so we have A. Then we okay, go from left to right, because plus is left associative. Remember, this is given that plus is left associative. Plus is left associate. Okay, so A you have. Then what you do? A plus A. So now you need to do A plus A. So now we have A plus A. Okay, next what we need? So this is done. See, this is done. This A plus A is done. So we have done this A plus A. Okay, so this is over. Next, what we need? Next we need again A plus A. This is already over. This we already have. This we already have. Now we need to do plus A. Now we need to do plus A. Now we have A plus A plus A. This also we have. Now this also we have. Okay, plus. Okay, but this we don't have. So again you have to do plus, so that you can create A plus A plus A. A plus A plus A plus A. Now we have this. Now we have this. Also we have this. So finally I can say that you do their plus. Now you do their plus. Okay, so you do this plus and this plus. Okay, now we have this expression. So what expression we have? We have A plus A plus A plus A plus A plus A plus A. This we have. Okay, next what we have? So now we have to do this A plus A. Okay, so this also we have to do. Okay, so this is the answer. Is this clear to everyone? Is this clear to everyone? So here, how many nodes you have? Okay, so you have finally 3. Okay, so 6 nodes you have. 6 nodes you have, and okay, 1, 2, 3, 4. Okay, 5, 6, 7, 8, 9, 10. So 10 edges we have. 6 nodes and 10 edges. Is this clear? Anyone has any doubt? Yes, it will be recorded. It will be recorded and available on the YouTube. This lecture will be available on the YouTube tomorrow. Okay, tomorrow morning you can find this lecture on the YouTube, on Go Classes YouTube channel. You can find it. Okay, so is this clear to everyone? Tell me, anyone has any doubt? Yes, of course, that is the meaning of the brackets. Yes, we see, you can't change the meaning of the expression. Okay, for example, okay, if I say a plus, okay, for example, if I say that 5 plus 5 minus 6 minus 2, okay, if I have this, don't change the meaning. Okay, of course, this should be done. For example, you have to do this. Okay, 6, 2, and then what you have to do? Then you have to 5 minus this. So this is your DAG, this is your DAG, and this is your abstract syntax tree also. Now, is this clear? So for example, if you have a minus b, now what is the abstract syntax tree? Abstract syntax tree will be a, okay, minus, and here minus a b. This will be the abstract syntax tree. Okay, and what will be DAG? What will be DAG? DAG is very simple. A, B, just do a minus b, and from this a, okay, from this a, you subtract this. This is your DAG. Is this clear? Is this clear? Anyone has any doubt? Anyone has any doubt in this? In this, do you have doubt in this? Ananya, do you have doubt in this? So what is the doubt? Tell me. What is the doubt here? See, this expression is already given to you. HP on DAG we perform optimization. For example, you have some intermediate code. On that intermediate code, we perform optimization. DAG is useful for some optimizations. Okay. Second iteration, I'm not getting. Yes, yes. You have, okay, optimization means improvement. Okay, so for example, you have some intermediate code. That intermediate code you are improving. You are improving that intermediate code. Are you getting my point? DAG, this is useful for some improvements. Okay, so using DAG, you can create a better, basically you can perform some optimizations very easily. We will see. For example, common sub expression elimination, that you can perform very easily using DAG. Okay. So what is okay, a plus a plus a. Let's see this. Okay, because left associative, it is given that it is left associative. Given that plus is a left associative. Plus is a left associative. What it means? What it means? It means a plus a plus a. This is same as a plus a plus a. Okay. So first you do a plus a. You have a. Now you do a plus a. Now this is a plus a. Now this node means a plus a. This node actually means, remember, this node actually means a plus a. And this node means a. Okay. Now you have to do this node plus this node. Okay. So this node plus this node you have to do. Yes or no? Is this clear? Is this clear? See, if we do this, then there is a problem. If you do this, then there is a problem. What this means? Can anyone tell me this is a DAG for which expression? This is a DAG given. Can you give me some expression for this? What is the expression? For which expression we are doing this? It means we have a plus a, we have a plus a, okay, and then we are doing a plus a. So you have a plus a, okay, and then you are doing a plus a plus a plus. So this DAG is for this expression. Is this clear now? This directed acyclic graph, is this clear? Now we have seen directed acyclic graph for expression. What we have seen so far, what we have seen so far, we have seen DAG for expression. If you have some DAG for expression, or I can say statement, okay, DAG for statement we have seen so far, okay. Now, so this we have seen so far. Now we will see what is DAG for basic block. What is a DAG for basic block? How to create DAG for basic block? Okay, so let's assume you have again the same. Okay, there is nothing here. The same you can do. Let me tell you how to create DAG for basic block. You have this basic block A equal to B plus C. Okay, then you have C equal to A plus X, and then you have D equal to B plus X, and then you have B plus C. Then you have, and then you have B equal to A plus X. Let me tell you, okay, how to do this. Okay, so very simple. See, these are initial value. Okay, see, okay, the method is actually value numbering. The method, let me tell you, the method is, okay, for both of them, the method is value numbering. Actually, here also we have done value numbering method. Okay, yes or no? So the method is value numbering. See, here also we have done value numbering. Yes or no? Here also we have done value numbering. If you see, can anyone tell me how did we do value numbering? We did value numbering during implementation. Yes or no? During implementation, we did value numbering. Value numbering means index. Yes or no? We use the index value. Yes or no? We used the index value during implementation. We did value numbering. Value numbering means index value we are using. Okay. So what it means? It simply means we are using array index, using array index. Okay. So anyway, let's see this question here. So you can notice that this, let's assume this is B0. Okay. So this is the initial value of B. So this is C0. Okay. Now this, okay, this I don't know, like, okay, let's call it A1. Why? Maybe initially some value was there. Now a value has changed. Yes or no? So let's call it A1. See, it does not matter actually. You can call it A0. There is no problem. You can call it, okay. There is no problem. You can call it A0. There is no problem. But why I am calling it A1? Why I am calling it A1? So that I want to say that in this expression, A has changed. Okay. Before this basic block, something was there. Something was there. Okay. Maybe A was there. This A, maybe this A is A0. Okay, so that is the reason I am calling it A1. But remember, this does not matter. You can call it A0, there is no problem. But let's call it A1. Now this and this, are they same? Are they same? Tell me, are they same? Yes, they are same. Now this is A1 and this is X0. Now this is C1. Now these are same. So this is C1. This is B0 or B1. Tell me, is this B0 or B1? Is this B0 or B1? Yes, this is B0. We are not changing B. Okay, this is D1. This is A1 and this is X0 and this is B1. Now this is B1. Yes or no? Is this clear to everyone so far? Very simple. Now very simple. See, first you do B0 plus C0. This is B0. This is C0. You do there plus. Okay, let's call it, here I am writing A1. Here I am writing A1, means this is A1. This is A1. Now what I need to do? A1 plus X0. Now I need to do, this is X0. Now I need to do A1 plus X0. I am calling it C1. Remember, C1 is this. This is your C1. This is your C1. Okay. Now I am doing B0 plus C1. Now I am doing B0 plus C1. B0 plus C1. I'm calling it D1. This is D1. Okay. This is a D1. Now what? Now what? So this is D1. Now A1 plus X0. Is it already computed? A1 plus X0. Is it already computed? Yes, this is already computed here. Yes or no? This is A0 plus X0. A1 plus X0. This is already computed, right? I told you don't compute already computed expression. Yes or no? Don't compute already computed expression. It's like this. It is like this. From initially what we have done. Already computed expression. See what you have computed expression. These are the computed expression. B0 plus C0. This you have computed. Okay. So this you have computed. A1 plus X0 you have computed. B0 plus C1 you have computed. Now don't compute this again. Don't compute this again. Is this clear to everyone? This is how you can create DAG for basic block. Again, the simple point, DAG for basic block. Okay, the DAG representation of basic block. The same point. Don't compute the already computed expression. Don't compute already computed expression. Okay. Remember, very important point. Remember, this B plus C and this B plus C, are they same? This B plus C and this B plus C, are they same? Are they same? Tell me, are they same? And are these two same? Are they same? Here answer is no, here answer is yes. Okay, here answer is no, here answer is yes. Okay, because you can notice that is the reason we are doing this. B0 plus C0. That is the reason I am giving in numbering. I am giving numbering. This is your value numbering method. I am giving number. Now you can notice this and this. They are different. Now you can notice they are different. But you can notice these two are same. These two are same. Okay, is this clear? Anyone has any doubt? Let's see this GATE 2021 question. This is your GATE 2021 question from DAG. Tell me what is the answer. Quickly tell me the answer for this. A equal to B plus C. This is the code that is given to you. And the DAG. The question is asking A equal to B plus C. A equal to B plus C. E equal to A plus 1. E equal to A plus 1. D equal to B plus C. F equal to D plus 1. F equal to D plus 1. G equal to A plus F. So what you will do? Very simple, very simple. All you have to do, let me tell you. Can you try? What is the answer? Can anyone tell me? See, this is B0, this is C0. Let's call it A1. Now this is A1. Let's call it E1. This is B0. This is C0. Let's call it D1. This is D1. This is F1. This is F1. And this is E1. And this is G1. Yes or no? Yes or no? Tell me. Yes, correct. Very good. Okay. So if you have done this, now the answer is very simple. So first B0, C0. Okay. Just okay. This is your B0 plus C0. Okay. Remember B0 plus C0 is already here. So you don't have to compute it here. Okay. You don't have to compute it here. So again, here actually you can write D1 also. D1 also you can write here. Okay. Next, what you have to do? So A1 plus 1. Now we have to do A1 plus 1. So actually you have to do A1 plus 1. So this is 1. You have to do A1 plus 1. This is your A1 plus 1. This is E1. Okay. Now next D1 plus 1. Okay. So what you have to do? You have to do D1 plus 1. So let's do D1 plus 1. This is your D1 plus 1. This is D1, this is plus 1, and this is your F1. Now we have to do this, and this is your G1. That's it. This is the answer. Okay, so now what is the answer? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so sorry, 7, right? 7 nodes. Correct? So total nodes are, okay, 3. Okay, so 7 nodes, and how many edges? 1, 2, 3, 4, 5, 6, 7, 8. 8 edges. 7 nodes, 8 edges. Is this clear? 7 nodes, 8 edges. The number of nodes. So the answer will be what? 7 nodes. In this question, the number of nodes will be 7. Is this clear to everyone? Yes, that is index. Nikita, that is index. See, I told you how implementation is done. How the implementation will be done. This is just an index. Means they are pointing to the same index. This is just an array index. Yes or no? When I'm writing like this, y plus 1 is different in node, because see, constants are also created as, see, these constants are, I told you, these constants are also treated as, you can say, as address. See, there will be, you can notice here, okay, you can notice here, we have done this previously. This you can notice, just notice this. There is entry in the symbol table. There is entry for the constant also. For the constant also there is an entry. Yes or no? See, is this clear, Nikita? See, there is an entry. There is an entry for constant also. Why not even F1 to the same? Okay, so for constant also we have entry. This is the entry for constant. What is the doubt? Why even F1? Why not even F1 to same node? Because they are not same. These and these are the same? Are they same? This is A1 plus 1. This is D1 plus 1. Are they same? Wait a second. A1 plus, okay, sorry, there is a mistake here. Oh, okay. Oh, sorry, there is a mistake. Okay, pardon me, there is a mistake here. Okay, so sorry for that. There is a mistake. Yes, okay, thank you for pointing out. So actually, okay, let me write like this: B1, B0, C0. Remember, these are indices. So this is your plus and this is your A1. Okay, next A1 plus 1. This is 1 and this is your A1 plus 1. Now you can notice that. So in this is your E1. Now E1 has this value, and you can notice A1 is D1. A1 is the same as D1. Okay, so actually D1 comma A1, they are same. Okay, so now you have D1 plus 1, that is also F1. Okay, now you have E1 plus F1, that is your, okay, so that is, so now, okay, now this is correct. Okay, so the answer is how many nodes? 3, 3, 6. Actually, 6 nodes will be there. Sorry for that. Okay, so 6 nodes will be there. Here, 6 nodes will be there. Okay, because you can notice A1 and D1 are pointing to the same index. They are pointing to the same index, A1 comma D1. They are pointing to the same index. Okay, so we have 6 nodes and 2 to, okay, so 6 edges. Okay, so now this is correct. Okay, so sorry for that. Answer is 6 nodes, 6 edges. Because actually these are also now these are also same. Now these are also same. Why? Because A1 comma D1, they are pointing to the same index. A1 comma D1 are basically pointing to same index. Okay, they point to same index. So this is correct now. Okay, so anyone has any doubt? Is this clear? Is this clear? Okay, so because they are pointing to the same, you can notice A1 comma D1, they are pointing to the same node. So that is the reason. E1 comma F1, so E1 comma F1 also point to same, point to same index, or I can say no, or I can say record. Okay, so this is your DAG, okay, directed acyclic graph. Anyone has any doubt in this? In the directed acyclic graph. Now, the directed acyclic graph is useful. The directed graph, cyclic graph is actually useful in common sub expression elements. This DAG, what are the use? What are the applications of DAG? What are the? There are many applications of DAG, but the applications of DAG, many applications are there. But the most useful expression is elimination of common sub expression. Basically, we are not computing the same expression again and again. Okay, if you have already computed something, don't compute it again. So that is the application of DAG, elimination of common sub expression. Okay, don't compute again and again. Is this clear? So in the last 3 lectures, we have already seen what is a basic block. So you know what is a basic block? No, Nikita, DAG is also created for the whole program. Okay, see, as I told you, abstract AST, abstract syntax tree, that is also created for the whole program. Okay, similarly DAG, that is also created for the whole program. Okay, similarly control flow graph is created for the whole program. 3 address code created for the whole program. Every intermediate code is created for the whole program. Okay, but we will only study how to create. We have only seen, we only need to see how to create DAG for basic block in the standard books also. If you see any standard resource, any standard book, they will also give you implementation. They will also give you how to create DAG for basic block, how to create DAG for expression, how to create abstract syntax tree for expression. Okay. Yes, that's the point. Okay. So for GATE exam only these are required. As I told you, I gave you some idea. Abstract syntax tree you can create for the whole program, but you don't have to worry about it. You only have to know whether you can create abstract syntax tree for expression also. For one statement, can you create abstract syntax tree? For one statement, can you create DAG? For basic block, can you create DAG? Okay. For basic block, you can also create abstract syntax tree. Okay. For this basic block, what will be the abstract syntax tree? How will you create? You can very easily create. See, okay, for this basic block, okay, let's take this basic block, a equal to b plus c, okay, and something like, okay, maybe, okay, something b equal to c plus d, a equal to, okay, something, a plus c, something, okay, anyway, okay, so whatever. So if you have this basic block, if you have this basic block, okay, then you create abstract syntax tree also you can create. The abstract syntax tree will be like this. Okay, so you have this block. Okay, in this block you have equal a, okay, plus b, c. Okay, there will be, again there will be equal b plus c, d. Again there will be equal, and there will be a, there will be plus, there will be a, there will be c. So like this you can create abstract syntax tree. Okay. Hello. Hi everyone. Am I visible? Hello, am I audible? Sorry, some technical problem. Okay, so is this clear? Now we have already seen in the last class what is basic block. Okay, so you already know what is a basic block. In the last 3 lectures we have seen what is a basic block, what is a control flow graph. Okay, so these things we have already seen, basic block and control flow graph. Okay, now in the control flow graph, what is a successor and predecessor? Okay, so basically this terminology we have to see, successor of basic block in control flow graph. Okay, in a control flow graph, if you have a control flow graph, in control flow graph, what is successor of a block? Okay, so what is successor of a block? Can anyone tell me? Very simple, like, okay, successor of block B. Successor of block B, what is that? That is set of, that is basically successor. Any block is successor, okay, if you have edge from B to B dash. Okay, so successor is any block to which you have edge from B. Okay, any block B dash such that we have edge, such that we have such that we have B to B dash, there is edge. Okay, so this edge is there. Okay, so for example, okay, and similarly predecessor, what is that? Predecessor of block B, what is that? Can anyone tell me? Predecessor of block B means any block from which there is an edge to B. Okay, any block B dash such that B dash to B there is edge. Okay, so this is the successor and predecessor. Is this clear? So for example, if you have this, okay, let us assume you have this block B1. Okay, and let us assume this is your block B2, and let us assume this is your block B3, and this is let's assume this is your block B4, and let's assume this, and let's assume this. So tell me, what are the successors of B1? Tell me, what are the successors of B1? Which blocks are successors of B1? Tell me, which are the successor of B1? That is B2, B3. B2, B3 are the successor of B1. What are the successor of B4? What are the successor of B4? Successor of B4 is B1. Okay, B1 is the successor of B4. And what is the predecessor of predecessor of B1? Predecessor of B1 is B4. And what is predecessor of B2? Predecessor of B2 is B1. And what is predecessor of B4? Predecessor of B4 is B2, B3. Is this clear? Predecessor and successor. Okay. So these PPTs, these slides will be available on the Telegram channel of Go Classes. Okay. Anyone who want to access these slides, who want to take these slides, okay, these annotated slides, if you want, then you can join the Go Classes Telegram channel. The link of Telegram channel is already available in the description of our YouTube videos. Okay, on the Go Classes YouTube channel, go to any video. Okay, in the description you will find the link for the Telegram channel of Go Classes. On that channel we put all the reading, all the study material. Okay, so these slides will be available there. Okay, so this is the point. Okay, flow graph. Is this clear to everyone? Successor and predecessor. Okay, so this is the idea. Next, a very important thing that I want to study, I want to teach you, okay, is that, so basic, in the basic block, what is the control flow? Can anyone tell me? Okay, I will see. Okay, Nikita, this lecture will be available. Okay, I will see that you can also access the previous material. I will check how to do that. Okay, so don't worry, we will check. So what is the control flow in the basic block? Inside a basic block, what is the flow? Can anyone tell me? If this is your basic block B, if this is your basic block, if this is your basic block B, then what is the flow? Can we have this type of flow? Okay, okay, in this flow is only sequential. This is the flow. Yes or no? Linear. Yes or no? Linear. Sequential. Okay, inside a basic block, only this type of flow we have. So inside a basic block, I can say, inside this basic block, I can say flow will be like this. Okay, so you can come from many places. This is your basic block. Okay, you can come from here also, you can come from here also, you can come from here also, you can go to this also, this also, this also, but inside this only this. For example, you can notice here, okay, here you can notice, for example, if you have block B1, okay, and you have block B2, let us assume, and then you have, okay, like this, okay, block B3. So you can notice that this type of thing. So inside only this flow will be there. Inside only this flow will be there. Inside a basic block, only this flow will be there. Okay, this is your control flow graph. I can say this is the control flow graph. This is the CFG. Okay, inside a basic block, this flow will be there. Remember? Okay, so inside a basic block, only this flow will be there. Okay, so this is the point. Let's see how to find basic block. That is clear to you, everyone. Now, the very important point that I want to point out. Okay, I will tell you. Can anyone tell me how many edges in the control flow graph? For this, first you find the leaders. What are the leaders? Can anyone tell me? What are the leaders in this program? You know what is a leader? Leader means first statement is a leader. You already know. So the first statement will be a leader. So the first statement is leader. Okay, so what are the leaders here? Can anyone tell me? Here, what are the leaders? Leaders, remember, first statement is a leader. Also, the target of, okay, the target of, you can say, the target of conditional or unconditional go to is a leader. Okay, so the target of go to is leader. So 3 is leader, 2 is leader, okay, and 13 is leader. So these are leaders. And what else? What else? The next statement of conditional or unconditional go to is leader. So this 10 is leader, this 10 is leader, 12 is leader, and there is no other statement. Else 18 also will be leader, but there is no other statement here. So these are the leaders. Yes or no? Is this clear to everyone? So these are the leaders. 1, 2, 3, 10, 12, 13. So these are the leaders. 14 is not a leader. Rasi, no, Nikita, 14 is not a leader. You know what is a leader? So this is the algorithm for leader. You can notice the first instruction is a leader. Okay, and you can notice any target of conditional or unconditional is a leader. So the target is a leader. And you can notice any instruction from the next instruction of conditional or unconditional is leader. Okay, so these are the leaders. Okay, so now you have leaders. Now, how many basic blocks you have? So number of basic blocks is equal to number of leaders. You already know number of basic, these things we have already seen in the last lecture. Okay, in the last 3 lectures we have seen number of basic blocks is equal to number of leaders. So these, how many leaders, how many basic blocks we have total? Okay, so you can notice 6 basic blocks we have. Okay, so what are the basic blocks? So you have basically these are the points you have. Okay, you have basic block B1. In this basic block B1, what are the statements? What are the statements in this basic block B1? Only statement 1. Okay, then you have basic block B2. In this you have only statement 2. Basic block B3. In this you have statement 3. Statement 3 to, okay, from where to where? Statement 3 to statement 3 to 9. Then you have block B4. In B4 you have 10 to 11. Okay, and then you have B5. Okay, so then you have B5 where you have what? So 6 we will, okay, so this is okay, so this, and then you have 3 to 9, and then you have 10, 11, and then you have 12, and then you have 13 to 7. Okay, B6, there is a B6 in the B6. What you have in B6? You have 13 to 17. Okay, so these are the basic blocks. Is this clear? Okay, so these are the basic blocks. Now you can just, okay, very easily create the, this will be your control flow graph. This is the control flow graph. Okay, in this control flow graph we have a special entry and exit vertex. Okay, start and end block to be ignored by default. Why ignored? Why ignored? Okay, so these are the basic blocks. So basically you have, okay, B1 to B1 total B6. Okay, B1, B2, B3, B4, by B5, B6. These are the basic blocks. Okay, and you can notice that if you have conditional go to, then how many edges will be there out of conditional go to? Tell me. From conditional go to, how many edges will come out? From conditional go to, tell me. From conditional go to, how many edges will come out? And unconditional go to, how many edges will come out? Can anyone tell me? unconditional go to and conditional go to. Here you have two successor. Here you have two successor. Here you only have one successor. Okay. Nikita, actually, let me tell you. Okay, here let me tell you. Many of the authors, okay, they put this exit and this starting and exit node. Okay, so even Ullman, this is from Ullman actually. This is from Ullman. So even Ullman puts this exit and entry vertex. Okay, so just count it. Okay, because most of the authors, many of the authors, they include this exit and entry. They have a special exit and entry. So total nodes will be, number of nodes will be 8. See, number of nodes in CFG control flow graph, that will be 8. Number of basic blocks will be 6. Number of basic blocks, that is 6. Okay, is this clear? No. So tell me here, tell me number of nodes and number of edges in the control flow graph. This is your GATE exam question, GATE 2015 question. Tell me the answer. So first you find the leaders. Okay, very simple. First you find all the leaders. So let me tell you what are the leaders here. What are the leaders? First statement is a leader, and the target of go to is a leader. So 2, 3 is a leader, and the next instruction is a leader. So this 10 is also a leader. Okay, so you have total 4 basic blocks. So total number of basic blocks is 4. Okay, number of basic blocks, that is 4. Okay, number of nodes will be 6. So automatically number of nodes in CFG, that will be 6. Okay, so you have total 4. Let me tell you, okay, what you will do. So basically you have B1. Okay, there is a B1. In this B1 only instruction. Okay, in this B2 you have this instruction. In this B3 you have how many instruction? From 3 to, in this B3 you have, okay, so 3 to 9. Okay, so 3 to 9. And there is B4. In this B4 what you have? 3 to 9. So basically you have 10, 11. Okay, so you have 10, 11. Okay, so these are the basic blocks, correct? Yes or no? 1, 2, 3, 10. Okay, so 1, 2, and then 3 to 9, and then 10. So these are the basic blocks. Now you can notice that from, okay, there is only one edge. There is only one edge here. And you can, because, okay, so because you can notice that B1 instruction is not a branch instruction. So there is only one edge here. From the instruction 9, how many edges will be there? From the instruction 9, how many edges will be there? There will be 2 edges. From the instruction 9, there will be 2 edges. There will be 2 edges, one like this and one like this. Okay, there will be 2 edges from the instruction 9. From the instruction 11, how many edges will be there? Okay, so one edge will be to 2. Okay, so one edge will be to 2. One edge will be like this. And okay, there is no other edge because there is no other instruction here. There is no other instruction here. So one edge will be to the, I can say, okay, to exit block. Okay, so there will be exit block. There is an exit block, and there is an entry block, and there is something called entry block. Okay, so this is the point. So basically 6 nodes you have. Okay, you have 6 nodes, and how many edges? You can notice 1, 2, 3, 4, and 5, 6, 7. So 7 edges. Correct? Okay, 1, 2, 3, 4, 5, 6, 7. Okay, so total 7 edges. So 6, 7. This will be the answer. Okay. Is this clear? So total nodes will be 6 and number of edges will be 7. In this, how many nodes and how many edges? Tell me. Find the number of nodes, number of edges. Tell me. Number of nodes, number of edges. Tell me the answer. First, you find the leaders. Okay. So number of leaders is very easily. So what are the leaders? Here the leaders, first statement is a leader, and the target of go to. So this L2. So this 7 is a leader. Okay. Because this target, this label L2. So this is a leader. Label L3. So this is also a leader. Anything else? Go to L1. So this L1, this 3 is also a leader. Okay. So you can notice this and this. Anything else? Is there anything else? And the next instruction, that is a leader. So this 5 is also a leader, and you can notice this 10 is also a leader. Okay, and this is just a halt. Actually, this is exit, so you don't have to worry about it. This is just exit. Okay, so okay, so this is just an exit actually. Okay, so you don't have to worry. Basically, this is your exit. Okay, so don't worry, you don't have to worry about this. Okay, so okay, these are the basic blocks. Is this clear? Okay, so actually 11, you don't have to worry about it. This is your exit, or you can say, okay, this is the exit. Okay, so this is just an exit instruction, so you don't have to worry about it. Okay, so actually leaders, I can say these are the leaders. Okay, so 1, 7, 3, 5, 10. Okay, 1, these are the leaders, right? Okay, so L2, this is L2, this is L2. L2 means 7. Okay, so the instruction number 7, this is a leader. And L3, okay, and this L1 means 3. So this 3 is a leader, and this 1 is a leader, and the 5 is a leader, and 8 is a leader. 5 is a leader, 5 is a leader, and you can notice 10 is a leader. 5, 10. Is this clear? Now, what is the number of edges? So total 5 basic blocks you have. Total how many number of edges? So you have total 5 basic blocks. What is B1? B1 is from 1 and 2. Okay, so these are the 2 instructions. What is B2? In B2, how many instructions you have? In B2, so that is 3 to 3,4. Okay, so 3,4. Then you have B3. Then you have B3. In B3, how many instructions you have? Okay, so 1, 3. Okay, so basically 5, 5, 6. So these instructions 5, 6. Okay, and then you have B4. In B4, how many you have? 5, 6. Okay, then you have 7, 8, 9. Okay, so 7 to 9. And then you have B5. And then you have B5. Okay, so from B5, how many? That is your 10. Okay, so in this you only have 10. Here you only have 10. Okay, is this clear? How many edges? So you can notice here the instruction number 2, this is a simple instruction, so only one edge will be there. Instruction number 4 is a conditional go to. This is conditional go to. You can notice this is conditional go to. This is conditional branch. This is conditional branch. So it will have 2 successor. So here you will have 2 successor. Okay, because this can be true or false. Okay, so one successor will be the line number 7. So here one successor will be line number 7. Okay, so you can notice 3, 4. Okay, so from this one successor will be line number 7. This will be one successor, and another successor will be this. Okay, line number 5. Okay, next after that you can see that, okay, what is the from 6? Okay, so line number, okay, so this is a simple instruction, so only this edge will be there. And then line, okay, this is again conditional go to. Again this is conditional go to. Then again 2, okay, 2, okay, from 9 to 10. Okay, one will be like this, and one will be to L3. L3 means basically, okay, exit block. Okay, one will be to the exit block. Okay, so from this 9, okay, one will be to the exit block. Go to L3. So this will go to the exit block. Okay, so from here you will go to the exit block. Okay, and what else? What about this go to L1? Can anyone tell me what about this go to L1? How many edges will come out from this? This is unconditional go to. This is unconditional branch. So only one successor will be there. Only one successor will be there, and that will be L1, means the instruction number 3. That will be instruction number 3. Okay, so that will be instruction number 3. So this is the point. Remember this. Okay, very important point I want to tell you. Don't put this edge. Don't put this edge. This is a mistake. Many students, they put these edges. I have seen. Okay, I have seen many students, what they do, they put these edges also. So remember, if you have conditional jump, 2 successor will be there. If you have unconditional jump, 1 successor will be there. Okay, is this clear? Is this clear to everyone? So if you have, okay, so I hope this point is clear to everyone. So this is a mistake that many students do. Okay, so remember, this is a mistake. Many students will make this mistake. This is wrong. Okay, this is wrong. So the answer will be what? So the answer will be how many edges? Okay, So tell me how many edges? 1, 2, 3, 4, 5, 6, 7. I think 7 edges. Okay, and you can notice there is an entry node. There is an entry. Okay, so 1, 2, 3. Okay, so 5, 6, 7. 7 nodes. Okay, 1, 2, 3. And then 5, 6, 7. Oh, sorry, how many edges will be there? Can anyone tell me how many edges? 1, 2, 3, 4, then 5, then 6, then 7, then 8. 8 edges will be there. Okay, so there will be 8 edges. For conditional, can we have more than 2 edges? We can have more than 2 edges actually, but not for conditional this if then HP. See, for the conditional statements, we cannot have more than 2 edges. For the conditional statement, for the because of go to statement, because of go to statement, only 2 edges can be there. Yes or no? If you have conditional go to, 2 edges will be there. If you have unconditional go to, 1 edge will be there. Okay. Yes or no? Is this clear to everyone? Tell me. Anyone has any doubt in this? So this is how you can create. Okay, so this will be your diagram, final diagram. So this is an important point. This what I want to say. This is important. Or I can say this is also misconception. For the go to, how can more than 2 edges will be there? Just think about go to statement. I'm talking about go to statement. See, let me tell you one more thing. That in your in your 3 address code. Okay, so this control flow graph has nodes. Okay, in this control flow graph, what is a node? Node is a basic block. Nodes are the basic blocks. Yes or no? Nodes are the basic block. What is a basic block? What is a basic block? This is a maximal. This is a maximal straight line sequence. Okay, this is a maximal straight line sequence of 3 address. Okay, 3 address code instructions. 3 address code instructions. Okay. For B5 to exit, why age is not taken? For B5 to exit, why this age should be taken? Unconditional. You have unconditional. HP, you have unconditional jump. If you are here, you will not go here. You will never go here. You will always go to B2 because this is unconditional. There is no condition here. So that is the point here. Unconditional jump. If you have unconditional jump, then you will always, for example, here, just look at this jump L1. Look at this jump L1. You will never go to this. This edge is not there. Why? Because you will directly jump to L1. Yes or no? See, is this clear? Is it clear? Because you have unconditional jump. There is no condition. You will directly jump. You will never go to the next block. For example, if you have this, okay, if you have jump, okay, jump 5, okay, and let us assume this is instruction number 8, and this is instruction number 9, like this, and this is instruction number 5, like this. Now you will always go here. You will never go here. Okay, so I can say from instruction 8, you will always go here. You will never go here. Yes or no? But if you have, okay, if you have, there is a condition. If, okay, if something go to 5, if you have this, let us assume. Now you can notice that. Now you can notice if this condition is true, then you can go here. If this condition is false, then you can go here. Is this clear? I hope this is clear now, because this is unconditional. Okay. That is last basic block. That is fine. There is no problem. There is no problem. This is the last basic block. We don't worry about it. This is the exit block. There is an entry block also. Okay, so you can point here. You can just write here. There is an entry block also, and this is the exit block. Okay, now, so exit has one edge from last block. Yes, 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 correct, Ananya. From the last block, from the last instruction, you have edge to the exit block. Okay, what is the last instruction? From that you have edge to the exit block. Okay, now we have already seen what is optimization. Optimization basically means improvement. Okay, so we are just improving the program. Okay, we are improving the speed of the program and also space. Okay, the space that is required. Okay, now my question is this. Remember, optimization, that is improvement, that is fine, you are basically improving. Okay, tell me this point, is this improvement? Okay, just tell me this point. My question, is this improvement? For example, x equal to 5 plus 8, this statement I am replacing with x equal to 13. Is this improvement? Is this improvement? Just tell me this point. Is this improvement? Yes, this is definitely optimization. I can say this is definitely optimization. This is definitely optimization. My question is this. Is this optimization? Is this optimization? Can I say this is optimization? Can I say this is optimization? Is this optimization? This is not optimization. This is not optimization. This is wrong. This is correct. Optimization should not change. Optimization should not change the meaning, the behavior, the semantics. Optimization simply means improvement. So this you can replace with this. This is improvement. You don't have to add. Okay, this is improvement. There is no problem here. But here there is a problem. Similarly, my question is this. My question is this. Is the following optimization correct? Can I replace this code with this code? Is this optimization correct? Is this optimization correct? Tell me. Yes, this is correct. Yes, this is correct optimization. Okay, see, okay, let me tell you again. Let me tell you. First of all, let me explain. First of all, remember this point. Okay, remember control flow graph. This control flow graph is created for each function. Is created for each function. Okay, so remember, if you have 10 functions, then how many control flow graph will be there? So if you have 10 functions, if you have 10 functions in program, if you have a program in which you have 10 functions, then it means 10 CFGs in program. Okay, is this clear? So the point is very simple. The control flow graph is created for each function. Okay, anyway, let me come back to this point. So, and you know what is a control flow graph? Control flow graph of a function, that is basically I can say nodes. You already know nodes are the basic blocks. Nodes are the basic blocks. You already know. Okay, and edges. What are the edges? Edges are the possible flow, possible control flow. Yes or no? Possible control flow. Correct or not? Yes or no? Possible control flow means the control can go from here to here. For example, here, look at here. This means the control can go from here to here. So this is control flow. This edge means flow, means from here we can go to here. From here we can go to here. From here we can go to here. So edge means control flow. Okay, possible control flow. So node is basic block and edge is basically possible control flow. Is this clear? Now let's come back to this point. Tell me, is this optimization correct? Is this optimization correct? Just tell me this point. Is this optimization correct? This optimization is correct. Let me tell you. This is not in syllabus, but this optimization is correct. Okay. At the compile time, you can do this. Okay. The compiler can do this. Okay. This is called, see this function. This function is unreachable. This is unreachable procedure. This optimization is correct, and this optimization is called unreachable procedure elimination. So if some procedure, if some function is unreachable, then eliminate it. Okay. So this optimization is called name of optimization. This optimization is correct. This optimization is correct. And this is the name of the optimization. Optimization name. This is the name of the optimization. What is the name of the optimization? Unreachable procedure elimination. If some procedure is unreachable, then remove it. Okay. So compiler can do this. This is not in our syllabus. In our syllabus, we only have three optimization. Only three optimization we have. Okay. We have dead code elimination, common sub expression elimination, and constant propagation. We don't have this in our syllabus. In our GATE syllabus, they have mentioned three optimization. Okay. Only three optimization they have mentioned. So this is not in the syllabus. But remember, this is correct optimization. In this optimization, you can notice that from this main program, this function is unreachable. So we can remove it at the compile time. The compiler can do this. Okay, the compiler can do this. So this is called unreachable code, unreachable procedure elimination. Is this optimization correct? Tell me. Is this optimization correct? Is it correct optimization? This is not correct optimization because we are calling F21. So, okay, so this is not a correct optimization. This is not a correct optimization. Okay, this is wrong. You can't do this. Okay, you can't do this optimization. Is this correct optimization? Is this optimization correct? Think about it and tell me. Is this optimization correct? Yes, this is correct. See, okay, this k square, this is not changing. Okay, this statement is not changing. See, this is not changing, but every time you are computing it, see, this k square, this is not changing in this loop. In this loop, this is not changing. But there is a problem. Every time you are computing this k square, every time you are computing this k square is not changing. K is not changing in this loop. Inside this loop, k is not changing. But what is happening? You are every time, if this loop is running 1000 times, okay, if you are running this 1000 times, then every time you are computing this. Every time you are computing this. So what you can do? You can take it out. Just take it out. Just take it out. Okay. This k square, you compute only once and you store in the T so that you don't have to compute again and again. Just think about it. If this code is running 100 times, then 100 times you are doing k square computed. 100 times you are computing k square. 100 times. So what you can do? What you can do? Very simple. Compute it once. Just take it out. Okay, just put it out. Okay, and okay, store this in T. Now this T you can use it here. So this optimization is correct. Yes. And what is the name of the optimization? This is called code motion. What is code motion? Okay, this optimization is called code motion. What it means? It means that you are moving the code outside. See, this code is not changing. This expression is not changing. So you can remove it. You can move it because this expression is not changing. So don't keep it in the loop. Just put it outside the loop. Okay. Is this clear to everyone? This optimization is called code motion. Code motion means basically if some statement is not changing, okay, find the code which is not changing. Okay, find code in the loop that produces the same value in every iteration. In every iteration, if you are getting the same value, then take it out. This code can be moved out of the loop. Okay, so that you do not have to compute again and again. So this is called code motion. For example, here, can we do code motion here? Tell me. Again, you can notice if this is not changing, if the length of the string is not changing, then take it out. If the length, okay, if the length is not changing, then what you can do? You can store string length in a, so that you don't have to call this function again and again. Okay, you don't have to call this function again and again. Is this point clear to everyone? Tell me. Okay, so this is the point. This is the whole point. So this is the code motion. Code motion means if something is not changing, then you can take it out. Okay. HP, the question that you are asking, this has been already taught in the C language. Okay, just look at the C language course. This is already C. Okay. Will this be a code optimization? It depends actually. Okay. what you are talking about, this x plus plus and x plus 1, okay, it depends on what is easy to do, and it depends on the machine. For example, okay, see, okay, let me tell you. For example, if okay, your compiler knows your target machine, yes or no? Yes or no? Compiler knows your target machine, correct? Compiler knows target machine. Your compiler knows the target machine because your compiler will create the code. Okay, now if on your target machine, on if on target machine, okay, if on target machine, let us assume uh, on target machine shift is if on target machine easier shift is easier than multiplication, okay, if this happens, then your compiler knows, okay, then what compiler will do, then compiler can do this. What your compiler can do, compiler can do this. What your compiler can do, tell me. Then compiler can do this. What, for example, if you have t equal to 2 into x, then your compiler will change it, okay, and it will, okay, it will just make this left shift, yes or no, some left shift something, okay, yes or no. So this left shift, something like this left shift, okay, left shift by 1, that means multiplying by 2, yes or no. So it depends on the target machine. Remember, this type of implementation is machine dependent. So this type of optimization, remember, this is important point. The optimization that you are talking about, that is machine dependent. There is something called machine dependent optimization. So this is machine dependent optimization. I hope this is clear, okay. But this optimization is not machine dependent. See, this optimization is not machine dependent. For example, this optimization is not machine dependent. You can do this, okay. Similarly, you can take this. Okay. Now, is this optimization correct? Tell me. This optimization, is this correct? Just tell me this point. This is not correct because the value of k is changing in the loop. Every time value of k is changing. So this optimization is not correct. In which phase of compiler do we do optimization? Can you tell me? In which phase of the compiler we, okay, like on where do we do optimization? This we have already seen. I told you. Where do we do optimization? Yes, in these stages we can do optimization. See, in these stages we can do optimization. On the pass tree we can do optimization. On the intermediate code we can do optimization. On the target code we can do optimization. This optimization is machine dependent. This optimization is machine independent. This is high level optimization. Yes or no? This is the best optimization because this is reusable. You can reuse this. This optimization you can reuse. All these points we have already seen. This optimization is machine dependent. This is machine dependent optimization. This is machine independent. Okay. And this optimization is high level. I can say this is high level optimization. This is also machine independent, but this is high level. Okay. So the best optimization is here. Here we have best optimization. We can use this optimization. This optimization is reusable. Okay. Now the next point is many students they have this confusion. Can anyone tell me in the last 3 lectures you have seen there is something called liveness analysis, live variable analysis? Yes or no? Liveness analysis. Liveness analysis. Another name is live variable analysis. Live variable analysis. Okay, so can anyone tell me this both are same, but tell me what is the difference between this analysis and dead code elimination? This analysis we are using for dead code elimination. Can anyone tell me dead code elimination? Dead code elimination. What is the difference? Can anyone tell me what is the difference? Is there any difference between these two? Is there any difference between these two, liveness analysis and dead code elimination? What is the difference? See, let me tell you, this is just analysis. This will give you some information. Remember, this liveness analysis will give you some information. This will tell you which variable is live, which variable is dead. Okay, I told you this in the last lecture. In the last 3 lecture, I told you this is analysis. This liveness analysis, this liveness analysis, this is just analysis. Means this will give you some information. Okay, this liveness analysis gives a certain insight, gives certain information about the code, about properties of the code. Okay, now once you have this information, once you have this information, now you can use this information to remove dead code. Okay, this information can be used. Remember, this information can be used for transforming our code to optimized code, to a improved code, to better code, by removing dead code. Is this clear? Is this clear to everyone? Tell me. Liveness analysis, this will give you some information. This liveness analysis will say which variable is live, which variable is dead. This will give you certain information. This will not do anything else, no transformation. Now this information, this analysis can be used for transforming our code to better code by removing dead code statements. Yes or no? Yes or no? Agree? Do you agree or not? This we have already seen in the last 3 lectures, but I'm again telling you that what is the difference between analysis, okay, and this. So you can notice this liveness analysis can be used for dead code elimination. What I can say, finally, I can say that this liveness analysis, these are the analysis. These are the analysis. For example, liveness analysis. For example, liveness analysis. For example, availability expression analysis. Available expression analysis. These are analysis. They don't do anything. They just give you some information. They will give you some information. Okay, this is liveness analysis, available expression analysis. Okay, some more in our syllabus we don't have. Okay, now what are the transformations we can do? Tell me the transformations we can do using these analysis. What are the transformations we can do? How can we change our program using? Okay, what this will help? Tell me. This will help in dead code elimination. Yes or no? Dead code elimination. Yes or no? This information will help in dead code elimination. So this is transformation. We are transforming our code into another code. Dead code elimination. Another use is register allocation. I will tell you, I will explain, don't worry. Another use is register allocation. This is another application. Available expression analysis. This is used in common sub-expression elimination. Common sub-expression elimination. This we have already seen in the last class. This we have already seen. Another use is copy propagation. Both these things we have seen. Okay, copy propagation. Yes or no? So these are the, so you can notice these are the analysis and these are the actual transformations. These are the actual transformations. Now let me tell you very important that optimization simply means do the analysis, then do the transformation. Is this clear? Optimization means do the analysis, based on that analysis, do the transformation. For example, do the liveness analysis and then do the dead code elimination. Is this clear? So the difference between analysis and all these things, are they clear? So optimization simply means analysis plus transformation. Analysis will give you some information, some insight. Okay, tell me what is the answer for this question. This is GATE 2014 question. Tell me the answer. So which of the following is false? So the answer is yes, this is correct. See, this live variable analysis can be used for dead code elimination. This is correct. Available expression analysis can be used for common sub expression elimination. This is correct. These two things we have already seen in the last lecture. Okay, I have already explained the complete details. I have already given in the last two lectures. Okay, and basic block is sequence of instruction where this is the correct definition of basic block. This is not correct. So can you tell me, is this correct optimization? Just tell me this. This is an example of common sub expression elimination. No, this is example of, this is called what optimization? This is constant folding. This is called constant folding. I have already explained this in the last lecture. Constant folding optimization. Yes or no? Correct. This is called constant folding. Okay. This we have already seen in the last class. Okay. So what are the type of analysis? So this also we have seen in the last class. What are the type of analysis? See, if you do analysis on within a single block. So for example, you have a control flow graph. Okay. So let's assume this is control flow graph of main. Okay. And this is control flow graph of F. Okay. So you have this is your control flow graph. This is the control flow graph of main. This is the control flow graph of F. Okay, let's assume. So this is the entry. This is the entry block, and this is the exit block. And this is the entry block, and this is the exit block. Okay, so now you can notice this is the control flow graph of main, and let us assume something like this. And let's assume here you are calling F. Okay, maybe you are calling here F. So basically this edge will be there. Correct? Yes or no? Yes or no? Yes or no? Okay, sorry. So yeah, so tell me, here you are calling F. So basically this edge will be there. Okay, so these are the basic blocks. Okay, so this is basic block B1, this is basic block B2, and so on. Okay, so this is the point. Now let's see. Now you can notice that if you do optimization within a basic block, you don't worry about this. Don't worry about this. Just worry about this. If you do optimization within a basic block, without worrying about other basic block, without worrying about these things, don't worry about these things. If you do optimization within a basic block, that optimization is called local optimization. So within basic block, that is called local optimization, local or peephole optimization. Okay. Another, if you do optimization within a control flow graph, within this, if you do optimization within here, okay, in this area, if you do optimization, or if you do optimization here, then that is called global or intra-procedural analysis. Okay, global or intra-procedural. Next, inter-procedural. What is that? Can anyone tell me? Inter-procedural. What is that? That is whole program. This whole program, this optimization. If you do optimization here, then that is called inter-procedural optimization. In our syllabus, we have local optimization. This is in syllabus. But this is in the syllabus, but we will see some of, okay, we will see some idea of it. We will see some idea. We will see some examples, so that if any question comes, then you can handle it. And this you can very easily skip. Without worry, you can skip. Okay. So this is your local optimization and so on. Okay. Next, also there is two type of analysis. One is data flow analysis, another is control flow analysis. Okay. Can anyone tell me, see the difference in the names? Control flow analysis means where the control is going from one basic block to another. Okay, where the control is going. For example, okay, let me ask you. Okay, control flow analysis will tell you where the control is going. Okay, from one basic block to another, the control is going, how the control is going. Okay, another is data flow analysis. In the data flow analysis, we worry about how the data is flowing, how the data is going from one place to another, one instruction to another, one basic block to another. Okay, so the data flow analysis, see, control flow analysis only worries about the control. So this is for your control, yes or no? This is your control flow. Age indicates control flow, yes or no? Age it indicates possible control flow, correct? Agree or not? So you can see age indicates possible control flow. So okay, any analysis which is based on this control flow, that is your control flow analysis. Okay, and similarly you can notice there is data flow analysis. How data is going, how data is behaving, how data is going from one basic block to another, how data is going from one instruction to another. This is called data flow analysis. Okay, so can anyone tell me, okay, just tell me this point, this analysis, what is this? This is data flow analysis or control flow analysis? This optimization is based on what? Control flow or data flow? This optimization, this is control flow. Very good, very good. Okay, so this is control flow, this is control flow analysis. Okay, also tell me, is this local optimization, global optimization, or inter procedural? What is this? This is inter procedural, intra procedural. What is this? This is control flow analysis, that is fine. What is this? Local optimization, global optimization, or the inter procedural? This is inter, not intra. See, this is inter procedural. There is a this procedure. There is no control here. This is inter procedural. Are you getting me this point? This is inter procedural, means whole program. Inter procedural means whole program. Inter procedural means whole program. So this is inter procedural and analysis optimization. Okay, now can anyone tell me what is the difference between unreachable code and dead code? Yes, this is inter. See, inter means, okay, I told you we create control flow graph. Okay, control flow graph is created for each function, yes or no? Is created for each procedure, yes or no? Each procedure. So for main you have control flow graph. This is control flow graph G1 for main. Okay, for main. And this is control flow graph for F. Now you can notice, okay, here you have something, basic blocks. Here also you have something, basic blocks. But you can notice there is an exit block, here there is an entry block, and here there is an exit block. Correct? There is an exit block. Here also there is an entry block, there is an exit block. So here also you have entry block, exit block. So this is your entry block, and there is an exit block. So actually there is no edge. There is no edge like this. Because there is no edge like this, so you can remove. Yes or no? Is this clear? Nikita, these every basic block is contains 3 address codes. Inside a basic block, what you have? Inside a basic block, what you have? Inside a basic block, you have 3 address codes. So all these are 3 address codes. We have 3 address codes, and this 3 address code is implemented. What are the implementations of 3 address code? Can anyone tell me? Implementation. Either you can use quadruple, okay, either you can use quadruple, or you can use triple, or you can use indirect tree. Is this clear? Yes. If man is calling F here, if man is calling F, if you have man is calling F, if here man is calling F, then there will be edge like this. From this exit node to entry node, there will be edge like this. If man is calling F. Okay, is this clear? So this edge is not there actually. See, this edge is not there. This edge is not there. So that is the reason this is unreachable procedure. This procedure is unreachable. We can't reach it. Okay, can anyone tell me the difference between dead code and unreachable code? Can anyone tell me the difference between dead code, comma, unreachable code? And is there any difference between dead code and unreachable? Dead code versus unreachable code. Is there any difference? No, these are not same. See, remember your TOC. In TOC, is there any state? Is there any difference between unreachable state and dead state? In DFA, okay, what is dead state and what is dead state and unreachable state? Is there any difference? Is there any difference between unreachable state and dead state? For example, okay, for example, tell me. Tell me here. Here, tell me. Just tell me this point. What is unreachable state? So you can notice this is unreachable state. This is an unreachable state. And this is dead state. So is this difference clear? Is this difference clear? Unreachable, comma, dead. So for example, dead code versus unreachable code. See, unreachable code, this is a property of control flow. This is the property of control flow. How the control is flowing. And this is the property of data flow. This is the property of data flow. Means whether data is used or not. Whether data is used or not. Whether data is further used or not. Is further used or not. So basically the difference is like this. Okay, let me tell you the difference like this. Dead code means like this. Dead code says that if you have some variable a equal to b plus c, will this value be used somewhere? Will you use it? Will you use it? Is there any use? Is there any use? Unreachable code means what? Unreachable code means what? Will you reach it? Unreachable code means will you reach it? Will you reach? Will you reach here? Will you reach here? Can you reach here? Basically, is it reachable? Can you reach here? Is this difference clear to everyone? For example, okay, this is dead code or unreachable code? Tell me. Here, tell me. Just tell me, okay, this example, take this example. Is this unreachable code or dead code? This, for this function f, this statement, is this unreachable or not? This is reachable, but this is dead. We are not using this value. Can you notice? This is dead code. See, this value we are not using. We are not using this value. This statement is dead. You can remove it. This is dead code. You can remove it because we are not using this value z. This assignment we are not using. Okay, tell me. Now this is unreachable. We cannot reach it. See, you will return from here. You will return from here. You will return from here. So now this is unreachable. You will never reach it. Okay. So the difference between dead code and unreachable code, is this clear to everyone? So can you notice dead code is unreachable code, that is property of control flow. This comes in the control flow analysis. This we study in control flow analysis. This we study in control flow analysis. And this we study in dead code analysis. Data flow analysis. This we study in data flow analysis. In our syllabus, what we have? Data flow analysis or control flow analysis? What we have? We only have data flow analysis. We don't have control flow analysis in our syllabus. You can check the syllabus. They have explicitly mentioned the data flow analysis. Okay. Is this clear? Now we will study live variable analysis. Basically, you have already seen this live variable analysis in the last lecture, but I will take many examples, many questions I will take so that you can handle all the questions. Okay. Many questions I am going to take. Okay. So we will take one break, but at this point of time, anyone has any doubt? Do you have any doubt so far? Did you learn something in this class? We have seen intermediate code. We have seen intermediate Y, okay, DAG. Okay, we have seen AST, abstract syntax tree, okay, directed acyclic graph. We have seen optimization and many things, basic block, control flow graph, okay, how to create control flow graph, basic block, and all these things basically. Okay, So do you have any doubt right now?